We're going to go ahead and begin the Introduction to Orbital Mechanics and Spacecraft Attitudes for Thermal Engineers course with Stephen Rickman. Stephen Rickman joined the NASA Engineering and Safety Center in January 2009 as the NASA Technical Fellow for Passive Thermal. In this capacity, he led a cross-agency technical discipline team, leveraging expertise from within and outside of the agency to solve high-risk technical problems and foster a community of practice for the passive thermal control and thermal protection disciplines. During his 35-plus year NASA career, his primary interest has been in the area of passive thermal control of orbiting spacecraft. Recently, his interests have focused on calorimetry of lithium-ion cell thermal runaway and thermal testing and modeling of wires and wire bundles to determine ampacity. He has authored or co-authored numerous technical papers and conference presentations, including public testimony given with the U.S. Air Force to the Columbia Accident Investigation Board. He authored a textbook chapter on natural and induced thermal environments. He was awarded a U.S. patent as the lead inventor for micrometeoroid orbital debris impact detection and location using fiber optic strain sensing, and another as a co-inventor on an innovative space station concept. Steve has received numerous mentoring, group achievement, tech brief, and Space Act awards, and has been honored with the NASA Exceptional Achievement Medal. From 2011 to 2015, he was an adjunct professor lecturer of mechanical engineering at Rice University, and he earned a Bachelor's of Science in Aerospace Engineering from the University of Cincinnati and a Master of Science in Physical Science from the University of Houston, Clear Lake. And before we go, please remember that there are going to be 4 scheduled breaks between the 5 different sections where we will be answering questions, and please use that time to check your phone, email. Please use this time as if you're physically in the session, so pay attention and do not have your phone, email. If you have not yet registered for the conference, please remember to register at the TFAWS2020 website. And during the presentation, if you have any questions, please post them to the chat on screen. And with that, Stephen, go ahead and take it away.
Thank you. Good morning, everybody. First, I want to give a shout out to Alex and Kayla and Carlos for helping make this session work this morning. I really, really appreciate it. And good morning, or good afternoon, and good evening, everybody, depending upon where you're joining from around the world. The first thing I want to do is welcome everybody to our Thermal and Fluids Analysis Workshop. Obviously, this year, we're doing it virtually because of the COVID pandemic. What my hope is that everything will tamp down, and next year we'll all be able to get together again. And should that happen, we're aiming to have the workshop in the Pasadena, California area, presented by the Jet Propulsion Lab. I also want to acknowledge the TFAWS co-sponsors, the NESC Passive Thermal Technical Discipline Team, which is mine, the Aerosciences Technical Discipline Team, the Environmental Control and Life Support Systems, and the Cryogenics Technical Discipline Teams, because all of them kicked in the resources to help make this possible. And of course, I just want to thank the whole TFAWS team and steering committee for making this event possible. This lesson is broken into 5 segments. And as Kayla mentioned, after each segment, we're going to take some time and answer any questions that you may choose to send in. About the halfway point in the course is actually after segment 2, at least halfway point in terms of charts. So we'll aim to take a break after the questions there, and it may be 15 minutes to a half an hour, we'll see. But everybody will get a chance to stretch their legs a little bit after segment 2. One of the things I was going to ask, just to kind of keep it fun, with regard to your questions, is when you're typing up your question, could you at least parenthetically add at the beginning of your question what city and state or what country you're joining from? We certainly welcome all of our visitors from around the U.S. and around the world, and it's just kind of fun to see where people are joining from. Okay, so with that, let's get into the subject for today, which is Introduction to Orbital Mechanics and Spacecraft Attitudes for Thermal Engineers. And some of you may have looked at the title and said, what does orbital mechanics and spacecraft attitudes have to do with thermal engineering? And we have to recognize that much of the work that we do is out in the space environment. And for those of you who've done any work with heat transfer in the space environment, you know a lot of what goes on with a spacecraft is driven by the thermal environment which it experiences. So when it's out in deep space, it may be experiencing the cold from deep space, the low sink temperature or the background radiation sink temperature. And it might also be getting sunlight on it. But when it's in proximity to a planet or a moon, it's picking up reflected energy, it's picking up outgoing long-wave radiation energy from the planet, and knowing where the spacecraft is with respect to that central body, whether it's the sun or whether it's the Earth or the moon, is really, really important to determine what the thermal environment is. What about attitudes? Well, depending upon how you're pointing a spacecraft will affect what environmental fluxes impinge on that surface. If you're pointing a surface towards the sun, it's going to experience a different environment than if you're pointing it towards deep space or if you're pointing it towards a planet. So how a spacecraft is oriented and where it is with respect to the heating sources and how it's moving with respect to those heating sources is of great interest to thermal engineers. What I would say is that many of us came up through our undergraduate coursework, and as we all know, there was plenty to learn during undergraduate, and perhaps you did not get an opportunity to get as deep into those courses or into that theory as you might have hoped. And then, like everybody else, you come out of school, you go into the job, and your employer rightfully expects you to start producing product very, very soon after you arrive. And there's really not as much opportunity as you might like to delve deeper into some of the theoretical aspects and some of the foundational things that are the underpinnings of the work that we do. So it's with that motivation that I put together this and other courses. I was telling Kayla before the course began today, I'm really glad that people benefit from these courses, but the truth of the matter is I put these courses together for me because I want to make sure I have a really good foundational understanding of what's going on. I'm happy to be here to share that with you today. So what I would invite you to do is take the next three or 4 hours, and let's just really focus in on the theory behind orbital mechanics and spacecraft attitudes so you can walk out of the course and have a better understanding for what goes on in the analysis tools and what goes on with the physics and what goes on during mission planning in your jobs. If you've been a frequent visitor to TFAWS, you'll know that I also teach a course called Introduction to On-Orbit Thermal Environments. This is the debut of the Orbital Mechanics and Spacecraft Attitudes for Thermal Engineers course. And some of you might have thought that this was just a complete redo of the earlier course. And I wanted to point out that while there's a decent amount of overlap between them, and I've tried to capture at least the main points, but certainly not all of the points here, I wanted to point out that the Introduction to Orbital Mechanics and Spacecraft Attitudes course really does focus down and in on the theory behind orbits. So you're going to see there is some overlap, but not as much as you might think given the title. I want to make sure I'm giving credit where credit is due. At the bottom of each slide where it's pertinent in the lower left-hand corner, I've got a list of links and references. So I cite them on each side. You're going to see some animations in here, and I developed those using a NASA program called Copernicus version 4.6. There's some other animations in here, and those are properly credited at the bottom, and then there's some Microsoft clip art scattered throughout the presentation. A couple of disclaimers. I use a lot of equations and physical constants in this lesson, and I'm going to say they're sound theory, they're good foundational theory. They've stood the test of time for hundreds of years in many cases, but I'm offering this up for instructional purposes only. And in some cases, they're going to involve some simplifications or approximations. And really, you should not use these numbers or these exact equations for design, analysis, or mission planning purposes. As a really good example, we're going to spend a lot of time talking about the two-body problem today. And we're going to talk about perturbations to the two-body problem, but I'm taking into account only a couple of perturbations. In reality, real mission planning takes into account a lot more, and it's a lot more of a precise art. That's something to really be respected and appreciated. So I'm not offering any of this up for design, analysis, and mission planning purposes. The other thing I wanted to point out is sometimes I use screenshots from analysis tools, and I want everybody to be clear that I'm not endorsing any particular tool. So just give you a little bit of introduction. Orbiting spacecraft are subject to a variety of environments, and you really do need to know something about how that spacecraft is moving through space, whether it's around the sun in a heliocentric orbit or orbiting the planet or a moon. You have to know those if you want to understand the environment. And I'm not going to go through all of these questions, but let me just pick a few of them. And I imagine as thermal engineers, you've run across one or more of these in your work. So for example, if you want to know what the solar flux is, if you're working on an interplanetary trajectory, how close or how far does the planet or spacecraft pass from the sun? How long, if you're going around a planet, how long does the spacecraft spend in eclipse during each orbit? What factors can make an orbit change over time, and how might that affect the thermal environment? So I'm not going to read all of these, but again, this is just a list of some of the questions that you might ask that are pertinent and of interest to thermal engineers. But orbit information alone really is not sufficient to determine how the environment affects the spacecraft. You have to know how the spacecraft is pointed. You can have the spacecraft in an orbit with a radiator pointed away from the sun or pointed away from the Earth. And that's a nice environment for the radiator. But if I have the spacecraft in the same orbit, but now the radiator's pointed towards the sun or towards the planet, then that's a different environment for the radiator. And as you can see, how the spacecraft is pointed or where the spacecraft is pointed is really, really important. So what we're going to do is we're going to focus on two things today. We're going to spend a lot of time, most of the lesson, focused on how do orbits work? What is the theory behind the orbits? How do things move in orbits with respect to the sun or with respect to a planet? And in the very last section, we're going to introduce spacecraft attitudes. What's really, really interesting about this, and it's really going to be part of the focus of the first section that we go through today, is a lot of the stuff associated with orbits and with attitudes can be handled with transformations. So if you think back to your undergraduate days when you learned how to multiply 3x3 matrices together, transformation matrices, a lot of that is the mathematical machinery that you'll need to be able to do both orbits and attitudes. The good news is if you're a bit rusty on that, we're going to have a quick review of it in the very first section today. So the scope of the lesson, of course, is orbits and attitudes. We're going to focus on the governing differential equation for first of what's called the unperturbed two-body problem. From that, we're going to show you, we're going to take that governing differential equation and we're going to squeeze it a little bit and show how the conservation of specific mechanical energy and the conservation of specific angular momentum pop out of it. Then we're going to go off and use that same equation to derive Kepler's laws. And then we're going to get into perturbations. In other words, it's not just the pure governing differential equation for the two-body problem. Now we're going to introduce some perturbing forces like an oblate Earth. There's other forces like drag and things like that we'll talk about just a little bit here. And then we want to talk about what the consequences are for the thermal environment. So the first part one, we're going to do a review of scalar, vector, and matrix operations. And this won't take too long, but I hope it'll serve as either a refresher for you if you haven't done this stuff in a while, or eventually when you download the charts, if you want to have a quick reference where you can flip through these and just get a quick reminder of how to do this stuff. So first we'll cover scalars and vectors. We'll talk about Cartesian coordinates, and actually we'll talk a bit about polar coordinates as well. We're going to remind you of what the vector dot product and what the vector cross product are. We'll talk about unit vectors, coordinate transformations, and coordinate transformations are really important to what we're doing today. And we're going to specifically look at the Euler angle sequence. And then we'll show you how to do rotation sequences using Euler angles, how you form a transformation matrix, and then how you stack those transformations together so that you can put a spacecraft through a pitch, yaw, roll, or a combination thereof. And in part two, we're going to focus on the two-body problem. I'm going to give you a little bit of terminology up front because the terminology, if you're not familiar with it, it's a little bit strange. And then we'll go into very, very, very brief history. There's much better accounts of this, but I'm going to introduce you to a few key figures. Then we'll talk about our strategy for how we're going to develop things there. We're going to show you Newton's laws and relative motion. And then there'll be another aside here where when you download the charts, I'll point out the chart when we get to it, but probably be a good idea if you dog-eared that page or wrote down that page number, because if you're ever scratching your head about any of the math that's shown in here, going back to this page, which gives you a useful expansion of some of the terms, will make you nod your head and understand where that came from. Then we'll get into conservation of specific mechanical energy and specific angular momentum. We'll talk about Kepler's first law and show you the consequences of that. There's a circular orbit, elliptical orbit, parabolic, and a hyperbolic orbit. And then we get into our first thermally related example where we're determining the solar flux using Kepler's first law. Then we'll do Kepler's second law, and we'll form an example where we determine how solar flux varies with time. Then we'll get into Kepler's third law. We're going to be determining the planet orbital periods using Kepler's third law, and then we'll apply that to geostationary orbit. Part 3 is going to give us an opportunity to look at perturbed orbits. The perturbed orbit is where the right-hand side of the governing differential equation is not equal to 0. So we'll talk about a number of different types of perturbations just at a top level, but we're really only going to focus on 2. One of them is a precession called the precession of the ascending node, and the example we're going to give there is the sun-synchronous orbit, and then precession of the para-apsis, and we're going to cover a type of orbit called the Molniya orbit. Then we're going to talk about the effect of orbit perturbations on the thermal environment. We're going to spend a decent amount of time on beta angle. Any of you that are spacecraft thermal engineers probably hear the beta angle being thrown about quite a bit, but it is so key to understanding what's going on in the thermal environment. It does bear our attention and spending some time on it. And if you have taken the introduction to on-orbit thermal environments, you'll notice that this is pretty much the overlap between that course and this course. But we'll calculate the beta angle. We're going to look at the variation of the beta angle due to seasonal variation and orbit precession. We're going to talk about some of the consequences of beta angle variation, like eclipse, calculating umbral eclipse entry and exit angles, how much time we spend in sunlight or eclipse. And then we've got a few examples there. One of them is eclipse season for a geostationary orbit. We'll talk about what a beta angle profile looks like for a space station orbit, and then we'll take a look at sun synchronous orbit and how flat the beta angle profile is for that. Then we're going to just at a top level cover advanced orbit concepts in part 4. We're going to do just a little bit of math in transfer orbit, and we're actually going to look just a bit more at conservation of specific mechanical energy when we talk about the transfer orbit. We're going to talk very briefly about orbit plane change and show you one calculation for that. And then just in a qualitative sense, I want to just make sure that you're aware of aerobraking, gravity assist, the restricted three-body problem, halo orbits, the orbit that's planned for Artemis 1, and also for this gateway outpost. None of the last handful of those have any math associated with them. They're just more for familiarization. Finally, in the fifth segment, we're going to shift our attention to spacecraft attitudes. We're going to talk about reference frames. For that, we need to understand what the body axes are for the vehicle of interest. We're going to look at the local vertical and local horizontal reference frame, the celestial inertial reference frame. We'll compare both of the LVLH and CI reference frames. We'll come up with an attitude transformation strategy, and we'll show you how to transform attitudes in celestial inertial and how to transform attitudes from the local vertical into the celestial inertial reference frame. Just a brief aside there, because we're going to need that in our very final example, is after you've transformed all of these attitudes, you really want to know what type of view factor the spacecraft surfaces have to the various heating sources. So there's a really nice general equation for a flat surface in an arbitrary orientation with respect to a planet that you can determine the view factor for. And then once we have all of that, we're going to tie everything together in an example where we do heating to a spacecraft surface as a function of orbit and attitude. After that, I'll just have a couple concluding remarks. I want to thank the people that are, that reviewed this lesson, and then I'll have some contact information there if you want to reach out and correspond after the lesson today. So let's start with part 1. This is our review of scalar, vector, and matrix operations, and I'm sure all of you have had this before, but if it's been a while since you've done some of them, I hope this serves as a good refresher, or again, and once you download and print out the charts from this lesson, it'll be good reference you can flip back to if you need to remember a specific detail. So the stuff that we're talking about here is stuff that we're going to need in our study of orbital mechanics and spacecraft attitudes. So we'll look at scalars and vectors. We'll look at Cartesian and polar coordinates, and then we'll do dot and cross products, unit vectors, coordinate transformations, with a particular focus on the Euler angle sequence. You're going to see that we use that quite a bit. And how do you form a transformation matrix, and then finally stacking those transformations so that you can get the attitude transformation that you wish. So let's first draw a distinction between scalars and vectors. Recall a scalar has a magnitude, whereas a vector has both a magnitude and a direction. And I offer as an example, speed is a scalar. And it has a magnitude only. So for example, you're driving down the road and you're going at 30 meters per second. But the difference between a scalar and a vector is that a vector has both a magnitude and a direction. So for example, a velocity is a vector that draws a distinction between velocity and speed. It has a magnitude and direction. So if you're driving down the road 30 meters per second in the x direction, if your road happens to be going in the x direction. So we're going to be using both scalars and vectors in our study of orbital mechanics and attitudes. So just a brief review of Cartesian coordinates. Each axis is orthogonal to one another, and at any point in the coordinate system, you can describe it by 3 coordinates, an x, a y, and a z value. And when you want to describe the amount of travel in each orthogonal direction, we specify unit vectors I, j, and k, where I corresponds to the x direction, j corresponds to the y direction, and k corresponds to the z direction. We'll talk about polar coordinates. They're going to be really useful in our discussion of orbits, but the way to look at polar coordinates is you want to find the location of a point. Well, let's see. You describe the location of a point using two parameters. It shouldn't be 2 points, 2 parameters, a distance from the origin, r, and an angle theta. So you can see in the example there, the point that's at the end of the vector r, I would describe that it's at some distance r and at an angle theta from the reference position here. So actually that should say using 2 coordinates, a distance from the origin r and an angle theta. When we talk about vectors, we can express them in Cartesian coordinates like this. If I've got a vector r, and let's say the vector begins at the origin, then the vector r is just some amount x in the I direction, some amount y in the j direction, and some amount z in the k direction. And if I want to know the magnitude of that vector, it's just the square root of the sum of the length of each of the coordinates there. So in this case, since the vector begins at the origin, it's the square root of x squared plus y squared plus z squared, just the Pythagorean theorem. Now let's take a look at some useful vector operations. For that, we're going to need a couple of vectors to work with. We'll define the vector r and the vector s, and both of those have their tail or their beginnings at the origin. So the vector r has got a magnitude of xr in the I, yr in the j, and zr in the k. And similarly for the vector s, it's got a magnitude of xs in the I, ys in the j, and zs in the k direction. They are separated by definition in this particular example by an angle theta, which is shown on the screen here. So if I have a dot product, if I take the dot product of 2 vectors, I'll remind everybody that when you take the dot product of something, that's a scalar. And we say that r dot s is the magnitude of r times the magnitude of s times the cosine of the angle between them. So for the vector shown at the right, it's simply multiplying the 2 x components together and summing them with the product of the 2 y components and the product of the z components. So it's very, very easy to take a dot product. When we talk cross product, we reminded that a cross product is a vector, and it's given by r cross s. It's the determinant of the 2 vectors. If you take a look at it like that. And I will point out that r cross s is not equal to s cross r. So just expanding on that determinant, you can see it at the bottom there. It's a little bit messier mathematically, but the important point to remember is that what you end up with is a vector. You end up with a vector that is perpendicular to both of the vectors that you have on the screen, or the vectors that are used to define them. Let's talk about unit vectors. As the name implies, a unit vector has 1 unit of length. So if you want to form a unit vector r, and unit vectors have kind of that little hat over them as opposed to the straight line, then you just take the vector r and divide it by the magnitude of the vector r. And what you end up with is a vector of 1 unit length that's pointing in the same direction as the vector r. So unit vectors are pretty easy. Let's talk about coordinate transformations. So if you're going to analyze a spacecraft in orbit in a specified attitude, you really need to understand coordinate system transformations. And we'll talk about what the overall strategy is when we get closer to that kind of work. But the position in orbit and the position with respect to heating sources and the eclipse is determined using coordinate system transformations. And then just to show you how prevalent this is, you do additional transformations to orient the spacecraft as desired at any given point in the orbit. So basically what you're going to see is kind of a spoiler alert at the end. You're going to see a whole stack up of transformations on some unit vectors, and that's going to put us where we want in our orbit and orient us where we want, or orient us with respect to the heating sources of the planet. And that's really all there is to this. So I just want to make sure everybody understands what the grand scheme is. When we do these transformations, we perform them as an Euler angle sequence. So an Euler angle sequence is a sequence of rotations of a rigid body with respect to a fixed coordinate system. It's order dependent. So if you change the order of the rotations, like an XYZ transformation isn't the same as a ZYX transformation, or roll pitch yaw isn't the same as pitch yaw roll, because it's order dependent. So we're going to rely on these Euler angle transformations considerably. The good news is that they're easily executed using multiplication of 3x3 matrices. Or if any of you out there like to program in a spreadsheet or some other math related program, you know, hopefully the light bulbs lighting up in your head saying, aha, I'm going to know how to implement this, and I'll be able to do all these calculations if I just put together a routine to multiply 3x3 matrices. So we need to be specific about the type of rotation that we seek. There are a couple possibilities here. One of them is rotation of the axes or rotation of an object relative to fixed axes. And I will confess, when I was putting this lesson together, I never really drew the distinction between them, but let me tell you, it makes a big difference here. And that's why I've gone into some detail on some subsequent charts here, because I need to point out what we're ultimately seeking here is a rotation of an object relative to fixed axes. I'll say it again. We ultimately seek a rotation of an object relative to fixed axes. So think of the fixed axes ultimately like as a celestial inertial coordinate system, and the object that we're ultimately going to rotate is a spacecraft. And then we're going to stack a whole bunch of transformations on attitude and where you are in your orbit and how the orbit's oriented and all that kind of stuff. We're seeking a rotation of an object with respect to fixed axes. So let's go look at this a little bit further. I tried to put together this illustrative example. So let's consider a two-dimensional Cartesian coordinate system, x to the left, y going up, x cross y is z out of the page. The z will become a little bit more pertinent when we get to the end of this derivation. But I just want to point out that the rotation that we're making here is about the z-axis. It's about the axis that comes out of the page. So let's look at the red vector p. We set it up as an angle at an angle phi from the x-axis in the fixed coordinate system. You notice I emphasize fixed coordinate system. And what we want to do is we want to transform this vector into what we're calling p prime. And we're going to do that by rotating it through an angle theta in this same fixed coordinate system. So I'm sounding like a broken record here because it's really important to emphasize that we're staying in the same coordinate system. So the problem statement here is, what are the coordinates of the tip of p prime? That is, what is x prime and y prime in terms of x and y? Okay. So if you get confused, come back to this page, and the very bottom two lines is our problem statement here. So let's look at this in a little bit more depth here. From the figure, we see that x is just equal to r cosine phi. So here's x right here. And that's just equal to r cosine phi. And then similarly, y is just equal to r sine phi. Okay. And then we can also observe in our prime system, or in our prime vector, x prime is just r cosine phi plus theta, and y prime is equal to r sine phi plus theta. And I will point out here that both p prime and r, both of those vectors are the same length, because all we're doing is rotating it. So that's why we can express x and y and x prime and y prime in terms of r. Now we're going to use some trigonometric identities. Let's take a look at these last two statements, the x prime and y prime, and look at them in a little bit more detail here. I can expand this using trigonometric identities, r cosine phi cosine theta minus r sine phi sine theta, etc. And I get the expressions for x prime and y prime in terms of these other parameters. And then since we already saw that x is equal to r cosine phi and that y is equal to r sine phi, we can just go ahead and substitute those in here. And when I group all of the terms together, you can see we can compress this into matrix form here. And now we have a nice expression that tells us what x prime and y prime are in terms of x and y. And the good news is this matrix here is the transformation matrix, the Euler angle transformation matrix that allows us to rotate this vector r into r prime by rotating it in amount theta. So we rotated P in the xy plane out of a vector or around a vector coming out of the page. And I mentioned earlier that is the z-axis, and it was a z-axis transformation. So we did it in 2 dimensions, but just recognize if we add this 3rd dimension here, any z dimension would have remained unchanged. And we represent that in the matrix by just multiplying it by, putting zeros in the rows and the columns and putting 1 in the appropriate place there. So the 3x3 analog to the 2x2 matrix that we just defined here is shown at the right, and that's our 3x3 z-axis rotation matrix, Euler angle transformation matrix. And then, as the math professors say, do the rest in a similar manner. So you can do similar operations and form the rotation matrices about the x and y axes. And again, this might be one of those pages if you're given to programming things in spreadsheets or math programs here, you might want to take note of this page here, because once you set up a transformation matrix multiplier, you can string matrices together all day and just multiplying 3x3s together and come up with the most complex transformations that you can imagine. Very, very powerful mathematics here that's very simply implemented. So we'll use shorthand later on because it's just a little bit cumbersome to write out 9 terms for each matrix here. So we're going to use this shorthand to represent the transformation of a vector. If I have a vector r and I want to transform it into r prime, then I use the rotation matrix that I need and multiply it together as I've shown down at the bottom. And if you want to do a series of rotations, you just multiply the 3x3 transformation matrices together, and I emphasize it here in the order in which they're to occur. So for example, if you wanted to transform r into r prime, do an Euler angle rotation first about the x-axis, then about a y-axis, and then finally about a z-axis, the matrix is just given by that. And it's that simple. So I'm about to wrap up part 1 here. If you've got some questions, go ahead and start sending them in here. But just to remind you, what we did is we established that many of the facets of the orbital mechanics and attitudes are interest to thermal engineers. And we also looked at key vector and matrix operations. We focused a lot on the Euler angle transformation because we're going to be using this as a toolkit for our study of orbital mechanics and attitudes. So at this point, I'll take a brief pause and see if anybody has any questions or comments.
Yeah, I don't think there are any questions for this section, so.
Okay, all
Part
right,
2.
that's fine. That's fine. All right, and if you do think of one, we will just tag it on to the question session for part 2. But I thought that was pretty basic. Hopefully it was just a review for something that you've already had. So let's get into some new material. We're going to start part 2 now, which is our focus on the two-body problem. I need to give you a little bit of upfront information because if you haven't worked with orbits before or haven't worked with them a considerable amount, then some of the terminology may be new to you or a little bit strange. So there's a lot of parameters involved here. So let's just take a look at the anatomy of an orbit here. I've set up an elliptical orbit about the Earth here. When we have an elliptical orbit, the central body, in this case Earth, is at one of the foci of the ellipse. The ellipse has some shape parameters associated with it. The first one I'm going to talk about is the semi-major axis, which is halfway distance from the high point of the orbit, which is called apoapsis, that is the maximum altitude of the orbit, and the minimum altitude of the orbit, which is called paraapsis. If you draw a line between them and take half that length, then that's referred to the semi-major axis, and that's denoted by the lowercase letter a. Let's see, the next thing I want to point out is that the orbit is tilted with respect to the equatorial plane of the body that it's going around, and the angle that it's tilted by is called the inclination. So it's the tilt of the orbit plane with respect to the equator, and that's denoted by the lowercase I. You're going to learn more about the shapes of the orbits as we go further here, but the more stretched out the orbit is, the higher the eccentricity is. So it describes the shape of the orbit, and we're going to talk about this a little bit more in the subsequent section. Let's see, let's look at some other points here. The orbit, there's a point at which the orbit crosses the equatorial plane going from south to north. And that is called, the location where that happens is the ascending node. And as a matter of fact, the location of that ascending node is going to be referenced to a coordinate system that we have not yet discussed, but let's just remember what the term is called. It's called the right ascension of the ascending node. And again, we're going to be discussing this in the subsequent section. Just remember that it's denoted by an uppercase omega. If we stay in the orbit plane now, in other words, if we move around the planet in the plane of the ellipse here, we can go to a point in the orbit where we reach the lowest altitude of the orbit, and that is called that's called paraapsis. And the angle measured in the orbit plane from the ascending node to where we reach the lowest point in the orbit is called the argument of the paraapsis. So that is represented by a lowercase omega. And then if we continue further in the orbit plane, we start out at paraapsis and we go to the location of the spacecraft as measured from paraapsis in the orbit plane. We call that the true anomaly. It's the angle from the paraapsis to the location of the spacecraft measured in the orbit plane. So we'll be talking about these and hopefully describing them a little bit more as we go through, but I want at least people to have an idea of what just the anatomy of a typical orbit looks like. One other thing I want to give you off to the side, because it's just an absolutely fascinating story, and I would encourage you to read some history of it. One of the books I refer to considerably during this course is Fundamentals of Astrodynamics by Bate, Miller, and White. If you're going to be doing any work with orbital mechanics or just want something that's absolutely fascinating and so well written, I'd recommend getting a copy of that for your desk. But the couple of the key characters here, Tycho Brahe, he was an outstanding observational astronomer, and he's known for just meticulously recording the positions of the planets. And actually, Johannes Kepler went to work for Brahe and used Brahe's data to fit geometrical curves to explain the positions of Mars. And I think the story goes that when he did this, when he fit circles, and it really was pretty close there, but Kepler kept pressing away at it. And had he not done that, we might not have discovered Kepler's laws as when he did. So that's for persistence. He gets a lot of credit for being able to not be happy with just a good enough fit. He took it a bit further, and as a result, we now have Kepler's laws. So he formulated 3 laws of planetary motion. The first one, and we're going to talk about all of these in more detail, is the orbit of each planet is an ellipse with the sun as a focus. His second law is the line joining the planet to the sun sweeps out equal areas and equal times. And his third law is the square of the period of a planet is proportional to the cube of its mean distance to the sun. Again, we'll spend a lot of time on these. The other important person in this development is Sir Isaac Newton, and there's a couple of his laws that are pertinent to orbital mechanics. First of all, his second law, where the sum of the forces is equal to the mass times acceleration, or the familiar F equals ma. And then his law of gravitation, which says every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So with that background in hand, we'll get on with the math. I will point out one other thing, though. Again, in Bate, Mueller, and White, absolutely fascinating stories just about how brilliant Newton was. So they give some really good historical perspective in there. And if you really want to just be fascinated by Newton's brilliance, I would encourage you to read the historical sections in this book. So here's our strategy. Using Newton's laws, we're going to derive the governing differential equation for two-body motion for an unperturbed orbit. In other words, it's going to be a body that's moving solely under the influence of gravity from a central body. We're also going to show that the specific mechanical energy and the specific angular momentum are conserved for the unperturbed orbit. And then from this, we're also going to derive Kepler's laws, and we're going to apply them in examples. That's kind of a nutshell version of what we're going to see in segment 2 here. Excuse me. So the governing differential equation for two-body astrodynamics, we can derive that if we start out with two laws from Isaac Newton. Newton's second law, F is equal to ma. And by the way, I'm going to color code here, so hopefully you'll be able to follow the various piece parts as we assemble them. So I hope that you'll find that helpful. And then Newton's law of gravitation, where that same force is going to be equal to or proportional to 1 over r squared distance between the bodies. And I just want to point out here, we'll learn about more of these terms here, but g is just a constant, is universal constant of gravitation. M represents the mass of the primary body. Lowercase m represents the mass of the smaller body. And then you notice some other r's floating around in parentheses to the right. And hopefully you'll remember from section 1 there, all that is a unit vector. It's a unit vector that points from one of the bodies to another body there. So don't let that extra r in the denominator fool you. We're just carrying it around because it's a unit vector. So one of the things we need to do is we need to define a reference frame for our calculations. And there is no absolute coordinate system, but we're going to create one here, and you're going to see that things are going to kind of fall out of it, so that we can set it up as quite arbitrarily, but it'll fall out of the calculations. But we're going to do this properly. The capital M is the mass of the first body. We're going to assume it's the larger mass. Lowercase m is the mass of the smaller body, and right here we're going to assume that lowercase m is much smaller than the uppercase m. R sub capital M is a vector from the origin of the reference coordinate system to the center of M. So you can see that here. Here's our reference coordinate system, and it's going to go to the center of M. The small rm is a vector from the origin of the reference coordinate system to the center of M. And r is the vector between m and m. And by the way, we're going to, spoiler alert, we're going to get that by subtracting one of these from the other. So in other words, this absolute coordinate system is going to drop out of here. X prime, Y prime, Z prime is inertial, and X, Y, Z is non-rotating. So X, Y, Z is the coordinate frame of this body. X prime, Y prime, Z prime is our fictional absolute coordinate system. And it's really important to remember that these are non-rotating with respect to one another, because it's going to let us make some simplifying assumptions as we go a little bit further into the derivation. So we see that if we subtract if we subtract r capital M from r lowercase m, we end up with our vector r between these two. So what's pertinent here is this big mass, this small mass, and the distance between them. And then we're also going to recognize that since x, y, z is non-rotating with respect to x prime, y prime, z prime, as I said before, the respective magnitudes of r and r double prime are going to be equal in both systems. So I want to be clear here. I'm not saying that r double prime is equal to r. What I'm saying is the respective magnitudes of r and the respective magnitudes of r double prime in both of these coordinate systems, the primed and unprimed coordinate systems, are equal. So that lets me say that r is just rm minus rm, like I did at the top, but it's also going to imply that the acceleration, r double prime, is just the difference between these, because it is a non-rotating coordinate system. So just want to make sure I'm very clear about that. When I'm applying Newton's laws, well, this is Newton's second law on the left-hand side. This is just mass times acceleration. And on the right-hand side, this is just Newton's law of gravitation. Right? When I combine those two expressions, I get r double prime is equal to minus this constant times the sum of these masses divided by r cubed. Now, some of you may be scratching your head and say, wait a minute, a second ago that was r squared. Again, this is, what I did is I pulled, remember parenthetically, this was r vector divided by r to give us a unit vector. We just pulled the r from the denominator in here, and that's why we have an r cubed. So just want to make sure you're following where the r's go. So if a spacecraft is in orbit about the sun, or even planets or other bodies orbiting the sun, the mass of the central body is just so much greater than the mass of the smaller body. You can neglect, or you can drop out that lowercase mass. And what you have then is the differential equation that just says r double dot plus mu over r cubed r is equal to 0. Okay. And I've noticed I've substituted mu here. Mu is just this universal gravitational constant times the mass of the central body. So you're going to see us use mu from here on out. So this is a really, really important equation that we're going to be using, and we're going to be squeezing and twisting this equation in various ways to learn an awful lot about what goes on in an orbit. I mentioned earlier that there's some useful expansion of terms. So again, if you're making notes here or you download the presentation, you might want to take note of page 46, because if you're scratching your head about any of the derivations that's coming up down the line, you're likely to get some better understanding by referring back to this page. Matter of fact, I went to another reference. This is a reference by Batten, Introduction to Orbital Mechanics, or Introduction to the Mathematics and Methods of Astrodynamics by Batten, because there was actually some things in another reference that I was seeing that were a little bit confusing to me. So I would encourage you, if you don't understand something when you see it, I would encourage you to seek out other resources, because chances are somebody's going to look at it from another angle, and you're going to have an aha moment, and you're going to have a better understanding. And the reason why I'm pointing this out here is because we've got a lot of terms that we can substitute in here. For example, when we talk about velocity, well, that's just r dot vector. And if we talk about acceleration, that's just v dot vector, which is r double dot. And where things got a little bit confusing for me is sometimes you're going to see r dot scalar, which is dr dt. And I want to point out that r dot scalar is not, I should say the magnitude of r dot vector is not just r dot scalar. I'll say it again. The magnitude of r dot vector is not r dot scalar, because there's other terms in here. So when you see that, just come back to this page here, and you'll be reminded that that things are a little bit more involved than you might assume. Here's another one here. R double dot, the magnitude of r double dot vector is not r double dot scalar. It's all of this stuff, or the magnitude of all of that stuff. So very, very important page. So I'd encourage you to make note of this, because you will want to come back to it. So the first thing we're going to do, as we twist and squeeze and turn this equation, is we're going to use it to show the conservation of specific mechanical energy. And the way you do that is you start out with the governing differential equation, which is in black here, and you dot it with r dot vector, which is in red. So when I do that, I'm going to put all of those terms in there. And of course, the right-hand side, r dot with 0 just goes to 0. So you're left with r double dot plus r dot mu over r cubed r is equal to 0. So let's see what we can learn with that. So now I'm going to color code these things. I'm going to rearrange it a little bit, and then we're going to take a look at the terms. The first term, r dot r double dot, we note that we can do an expansion of that below. And gosh, you got to really give credit to the people who originally derived this to be able to see this in there. But basically, r dot r double dot is just equal to, if you go all the way over to the right, 1/2 d dt of v dot v. And then if you look at the orange term, 2 r dot r dot r, that's just equal to 2r dr dt. Okay, so when we've got those substitutions, we can put those back into our original equation and do a little bit of reorganizing, and you can see things are getting a little bit simpler at bottom. You notice one of the things there is that both terms have a derivative with respect to time in them. And what that tells me, well, let me do a little bit more rearranging and simplifying here. What it tells me is that it's just begging to be integrated with respect to time. I will point out here, if I've got terms that when you differentiate them with respect to time, it's equal to 0. As you know, when you integrate things with respect to, if you integrate 0 with respect to time, what you end up with is constant here. And not only do you end up with a constant, but what you're talking about here is the energy, because you can recognize that the first term is just the kinetic energy per unit mass. You know, think of it as kinetic energy is 1/2 mv squared. So if you divide out the mass, this is just the kinetic energy per unit mass. And it turns out the second term is the gravitational potential energy per unit mass. And what it says is that those add up to a constant value all over the place. Now, later on, this is a spoiler alert, when we get to our brief discussion of transfer orbits, we're going to derive another expression for specific mechanical energy. And again, you're going to see it's constant. And aside from the mu term, it's going to be a function only of the semi-major axis of the orbit. And since the semi-major axis of the orbit stays constant for the unperturbed two-body problem, again, the energy is constant for the orbit. Okay, so we've looked at conservation of specific mechanical energy. We also looked at the conservation of specific angular momentum. And again, we start out with our governing differential equation, but this time what we're going to do is we're going to twist it and turn it a little bit differently. We're going to take the cross product of r with this equation. And you notice when we take a vector cross with itself is 0. And let's take a look at pointer here. You notice r cross r is equal to 0. That just leaves us with r cross r double dot is equal to 0. So the nice thing about this may look a little bit messy, but the terms drop out. So r cross r double dot is equal to 0. And then we also note that, see if we like r cross r double dot, well, that's actually part of a bigger term. And again, I really give credit to the people who derived this the very, very first time, because if you look at this as part of a larger term, you realize you can express it in terms of ddt of r cross r dot, because the good news is when you expand that, term, the r dot cross r dot term drops out because r cross r dot is equal to 0. So you can say that ddt of r cross r dot is equal to term that we originally cared about, and that's equal to 0. Well, just like we did before, we noticed that there's a term in there that's a derivative with respect to time, and that's equal to 0. But furthermore, we recognize that r dot vector is just v, the velocity, is equal to 0, and you recognize that r cross v is equal to the specific angular momentum, right? It's the angular momentum per unit mass, or if you think of angular momentum as r cross mv, so you divide out the m, it's the specific angular momentum. So you notice when you integrate that, you get r cross v is equal to a constant. So here we have shown that the specific angular momentum is a constant, and we call specific angular momentum the lowercase vector h. Okay, so now that we have the governing differential equation, we've shown conservation of specific mechanical energy and specific angular momentum, we can move on to deriving Kepler's laws. So Kepler, his first law says the orbit of each planet is an ellipse with the sun as a focus. And I put an asterisk next to that because he was talking about the planets, but really this governing differential equation does so much more than that. There's other orbit shapes that are possible, and these are described by what are called the conic sections. So let's take a look at what's a conic section. So I've drawn a right circular cone 4 times on the right-hand side, and I've cut it with a cutting plane in different ways here. So if you take that right circular cone and you cut it with the plane at different angles, the shapes appearing at the cutting plane are also the shapes of orbits. So on the upper left, you cut it at an angle, then you have a parabola. If you cut it straight up and down, you have a hyperbola. Actually, it's often shown with a cone pointing upwards as well. And when you cut it, you end up with a hyperbola of two sheets. Then if you cut it parallel to the base of the cone, you get a circle. And if you cut it at an angle to the base, then you get an ellipse. So all of these are solutions to this governing differential equation. That's kind of the spoiler alert there. So let's go ahead and derive Kepler's second law. Again, we always go back to the governing differential equation. I will confess that as an undergraduate, a lot of times we'd see a professor go off and derive a governing differential equation, and then I'd kind of shrug my shoulders and say, okay, well, that's good. Now what do I do with the equation? So here, I try to emphasize that all of these derivations we're doing, we're starting out with the governing differential equation, and you saw conservation of angular momentum and saw conservation of specific mechanical energy, and now you're going to see all of these really wonderful things pop out of this governing differential equation like Kepler's laws. So we start out with that, we rearrange the equation, and then what I want to do this time is I want to form a cross product with the angular momentum vector. So all I'm doing is crossing the left-hand and the right-hand terms there, and then in the very bottom, I wanted to get rid of the minus sign, so I switched the R and the H terms so that I could get rid of the minus sign there. So let's take a look at this in more detail here. So again, I've color-coded it. Left hand's red, right hand is green. So if I expand that left-hand term, that R double dot cross H, you notice I can do that as R double dot cross H plus R dot cross H dot. And you remember that since we have a conservation of specific angular momentum, the specific angular momentum doesn't change with time, so that H dot term is 0, and I'm left with a term d dt of R dot cross H. If I look at the right-hand term, I can expand the momentum term there, H, into R cross V. And you notice I've shifted to blue there because I'm going to do some work with that. And the R cross V cross R with the triple vector, I think it's triple vector product, I can express that in an equivalent expression on the right there. And then if I look further into that triple vector product, on the far right-hand side, I've gone from blue to purple. You notice I have an R dot V term, and I can expand that. And this is where all of those derivations on page 46 are helpful. There, that R dot V term actually becomes R dot scalar. And long story short, when you do all that, you end up with the expression at the bottom of the screen. And then if you do some additional simplification, you end up with the expression at the top. And then when I marry that back with the simplifications we did with the red term, then I've got ddt of R dot cross H is equal to mu times ddt of that unit vector. Okay. So I'll just repeat that convenience. And then when I integrate that above equation, because again, it's just screaming to be integrated. So we're integrating it with respect to time. I get R dot cross H is equal to mu times, that's the unit vector, plus a constant. And that constant, if we're integrating vectors, we end up with a constant vector. And that's called, if anybody wants to take note of it, it's called the eccentricity vector. And just interesting factoid, that would point from the center of the central body out to the point in orbit, the low point in orbit called the paraapsis. Okay. So now if I dot both sides of the equation with the vector R, I end up with the expression that I have up there. And again, this is just a lot of being able to see the forest through the trees, going through all of those simplifications there. That magenta term just ends up to be the magnitude of the angular momentum squared. The blue term ends up just being mu times R, and then I guess it's kind of the orange term, R dot B is just equal to R times B times the cosine of nu. Okay. And then that just simplifies to the expression that we have there, again, maintaining the color code. And when I rearrange it, I get an expression for r as a function of all of these parameters. So let's stop and look at that for a second. Maybe that looks a little bit familiar. And hopefully it does. If I were to hold this form of this equation up against the general equation for a conic section in polar coordinates, we see some similarities. The orange terms correspond to one another. The blue terms correspond to one another. The general form of the equation looks the same. And in this case, if you recall earlier, I talked about the semi-major axis A. We're using that here, and E is the orbit eccentricity. So what I did is I started with the governing differential equation, and I derived something that is very familiar in form as it represents the equation of a conic section in polar coordinates. So now that I see that, I can kind of equate what I'm calculating to the orbit parameters of interest here. And what it tells me is that that form of the equation, it confirms that when you derive an orbit under these assumptions, it takes the shape of a conic section, and the shape is dependent upon the orbit eccentricity. So when I have eccentricity of 0, I have a circle. When the eccentricity is between 0 but less than 1, I have an ellipse. When it's equal to 1, I have a parabola. When it's greater than 1, I have a hyperbola. And let's take a look at some of the orbits representing each orbit type. So first one I want to talk about is a circular orbit. It maintains a constant distance from the central body. This is where the eccentricity is equal to 0. I have a space station here, and admittedly, I don't have it flying in the orientation that it usually flies in here. I did look up the eccentricity of the station orbit a few days back, and they reboost it from time to time. But it was 0 out to about 3 decimal places. I think it was like 0.0005 or 0.0009 in that range there. So I would say that's pretty close to being circular. There's many Earth satellites that have circular orbits, and as I pointed out, the International Space Station is in a circular orbit. If you are into astronomy, you can go out and look at comets, and many comets are in elliptical orbits. This where the eccentricity is between, it's greater than 0, but it's less than 1. And it traces out an ellipse with the central body as one focus. So for comets, the sun is the central body. And as an example, Comet 103P, P meaning periodic, Hartley 2, they're in elliptical orbits, and Comet Hartley 2 has a period of 6.46 years. And if you want to know what kind of eccentricity that comes out to be, it's an eccentricity of 0.694. So it's very, very far away from a circular orbit. Parabolic orbits, and I wanted to look this up here because if you think about it, as we go to the hyperbolic orbits, you see hyperbolic orbits aren't bound to the sun, whereas anything less than an eccentricity of 1 is bound to the sun because it repeats. Eccentricity of 1 is just kind of right on the hairy edge of it. It has just enough energy to come into the orbit the sun and then go out, and then if it was any more energy, it would escape in a hyperbolic orbit. If it was any less energy, it would come back in a very, very, very long ellipse. So I wanted to get you a quote here. It's with an observational uncertainty. Long-term comets all seem to have parabolic orbits, and it suggests that they're not truly interstellar, but are loosely attached to the sun. They generally classified as belonging to the Oort cloud on the fringes of the solar system at distances estimated to be 100,000 astronomical units. So like I said, it's just on the hairy edge. A little bit less energy, it would be captured as an ellipse. A little bit more energy, it would be lost forever in a hyperbolic orbit. Speaking of hyperbolic orbits, a few years back, the very first asteroid of interstellar origin was discovered. I'm not going to attempt to pronounce or mispronounce the name, but you can see the orbit right there. I think since then another one may have been discovered here, but it basically had so much energy that it wasn't bound to the sun. It made one passage through the solar system and then it's gone. And as you can see, based on measurements that they made, the eccentricity is greater than one's like almost 1.2. So that asteroid's not coming back. Okay, so now that we've looked at Kepler's laws, excuse me one second. Now that we've looked at Kepler's laws, let's go ahead and apply it to an example. And we saw that the equation is the same form as the general equation for a conic section in polar coordinates. And we talked about the semi-major axis and the eccentricity. And nu is the true anomaly, which is the angle measured in the orbit plane from the para-apsis, or the closest point to the central body. So for a planet orbiting the sun, r is a minimum. We call that, when it goes around the sun, we call it perihelion instead of para-apsis, when nu is equal to 0, and r is a maximum, call that aphelion, when nu is equal to 180 degrees. So let's take a look at what kind of solar flux values you have based on distance from the sun. So if you were to go out into space at Earth's mean distance from the sun with a radiometer and measure the intensity of the solar flux, then on every square meter of surface, you would see somewhere in the neighborhood of 1,371 watts of power falling on it. So we say that the flux is 1,371 watts per square meter. I've seen other publications that say 1,367, so use your favorite, but it's right around there. And if we want to take a look at the solar flux at any distance, and we do this measured in astronomical units, we note the following. You can just plug in the value at different astronomical units and be able to calculate the solar flux. I go into more detail on this in the Introduction to On-Orbit Thermal Environments course, but it's just basically a conservation of energy calculation. The same amount of energy emitted from the sun has to be crossing spheres of any radius as you get further and further away from the sun. That's what gives rise to the R-squared law. And this is a very simple formula that will give you an opportunity to calculate the solar flux at any distance. So I went ahead and did that, looked up the semi-major axis and eccentricity data from the National Space Science Data Center. The link is at the bottom there. I put the semi-major axis and the eccentricity. That lets me calculate perihelion and aphelion distance. And it also lets me, and the formula on the previous page, lets me calculate the solar flux at perihelion and aphelion. So if you've done any analysis of spacecraft orbiting Earth, you'll notice the values, the perihelion and aphelion values should look familiar to you, somewhere around 1418 for perihelion and 1320 something for aphelion. By the way, and we talk about this in the Introduction to On-Orbit Thermal Environments, the perihelion actually occurs on or about early January. I want to say somewhere close to January 4th of each year. And the aphelion, or the minimum solar flux value, occurs somewhere on or around July 4th of each year. And I realize we perhaps have people tied in from all over the world, but the way I remember it is just for those in the United States that celebrate Independence Day on or around July 4th, and you're sitting out at a picnic and it's just so hot out, you can tell everybody around the picnic table, yes, but did you know we're pretty much at our furthest point from the sun on this day? And they'll probably think you had too much heat and offer you a cold beverage. What's really, really interesting here is just the variability that you get, or variation you get. Look how hot, or look how much solar flux you get at Mercury compared to how much you get out at Neptune. And then you can see the variability. You know, there's obviously a lot of interest in Mars. Look at the variability you get throughout a Martian year of the solar flux value. So very easy calculation to do. If you ever wondered why it varied, this is the reason why. The same formula, I will point out, you can certainly use for interplanetary spacecraft. So if you've got a spacecraft going between Earth and Mars, and you know the distance from the spacecraft to the sun on any given date in astronomical units, you can put in that as your R value and calculate the solar flux that's incident on the spacecraft. So if you're doing an interplanetary thermal analysis, it's a very, very easy thing to do, and it lets you vary the solar constant or the solar flux throughout your transit period. Okay, let's move on to Kepler's second law, which states that the line joining to the planet to the sun sweeps out equal areas and equal times. So if you notice here, I've got a spacecraft orbiting here. You notice it moves faster as it gets close to the planet, and it moves slower as it gets further and further away from the planet. And if you were to look at the angle that's swept out by that spacecraft over time, the angle being measured from the center of the central body to various points on the trajectory there, in this example, I've got areas A1 and A2, and they happen to be traversed in the same amount of time. In other words, delta T1 is equal to delta T2. So those are mapping out equal areas or sweeping out equal areas in equal times. It's called constant areal. That's A-R-E-A-L, not aerial, A-E-R-I-A-L, areal velocity. It's moving with a constant area per unit time. So let's take a look at deriving that. Remember, we derived expression for angular momentum. And again, I'll refer you back to page 46. The expressions for the vectors r and v. So we can expand on those a little bit there with the expressions that we had from page 46. And if I want to look at the expression for h, I can just take the determinant r cross v, or the determinant of r cross v is that there, and I ended up with r squared d theta dt. Okay, and the magnitude of that vector is just r squared d theta dt. So we showed previously that the specific angular momentum vector is constant, and if we recognize that the area swept out over time is simply just 1/2 of the specific angular momentum, in other words, angular momentum is r squared d theta dt, and if we calculate the area swept out over time, it's just 1/2 of that value. And if the angular momentum is constant, then the area that's swept out over time is also constant. So that's one way of showing it. Now, may scratch your head a little bit, so let's show how to derive it another way. I found another reference down at the bottom here that does it another way here. Let's take a look at the area, or differential area. It's just 1/2 r dr sine alpha. And if we let the differential area dA be represented as a vector, then you recognize r dr sine alpha is just r cross dr. That's the convenience of representing it as a vector. And if you differentiate that with respect to time, you get 1/2 r cross r dot. And if you differentiate again, you get a double dot, and that's just equal to 1/2 r cross r dot. And look at what happens when you expand that. A vector crossed with itself is 0. And turns out when you got vectors pointed in the same direction, that's also 0. So we know that dA dt is equal to a constant, right? Because if you integrate a double dot, and if a double dot is 0 and you integrate that, you get a dot, I'm sorry, dA dt, which is a dot, and that's equal to a constant. So using Kepler's second law to determine how solar flux varies with time. I showed you before that if you know the shape of a planet's orbit, the aphelion and perihelion distances, and you know the solar flux at 1 astronomical unit, you could use that to determine the minimum and maximum solar flux. But now we want to calculate temporally how the solar flux for Earth varies throughout the year. And what I'm going to do is I'm going to do two approaches here. One of them is I'm going to compare a simplified model where the Earth moves around the sun at a constant rate versus what the true solution would be if we employed Kepler's second law. Remember, a consequence of Kepler's second law is that you have to sweep, or that it sweeps out equal areas in equal times. So when you've got a planet, moon, or spacecraft orbiting a central body, it's got to move through its orbit faster at some locations, slower at others, if you recall that video that I showed you. In other words, the angular rate at which the orbiting body moves around its orbit changes depending upon where it is in orbit. Okay? So let's look at two ways of calculating the solar flux variation for Earth. The first thing we're going to do is say, let's assume that Earth moves around the sun at a constant rate. Well, we know the Earth makes one circuit of the sun in about 365.25 days. Actually a little different than that, but that quarter day, gives rise to our use of leap years. If Earth's orbit sun were circular, then the angular rate would be constant. And I would say that you'd go through 360 degrees over 365.25 days, which is about 0.986 degrees per day. So in other words, on average, the Earth progresses around the sun about a little bit less than 1 degree per day. But Earth's orbit around the sun isn't circular. It's almost circular, but it's not quite circular. It's slightly elliptical, and the eccentricity is 0.0167. So if you look at that and compare that with the eccentricity of a circular orbit, you will see that a circular orbit has 0.0,
This is just slightly off of that. And this is what gives rise to the aphelion and the perihelion distances and the variation in the solar flux that we saw. But remember, because of Kepler's second law, because it's slightly elliptical, the angular rate is going to vary dependent upon Earth's distance from the sun. So what I did here is I calculated the solar flux progression with time as Earth moves around the sun. And the good news here is that even for Earth, when you've got an eccentricity of about 0.0167, the approximation is not too bad. Matter of fact, the curves are almost on top of one another. The blue curve represents the solar flux based on the true progression of Earth's orbit about the sun, whereas the red one is based on the mean progression. So if you were doing analysis, that's probably not a terrible difference, but it doesn't work well for planets with more eccentric orbits. So let's take a look at Mars. Mars has an eccentricity of close to 0.1, okay, which means it deviates from the circular orbit, which means there's more of a pronounced variation in the area swept out, more pronounced variation in the speed of the planet when it's closer to the sun than when it's further away from the sun. So again, I use the blue curve to represent the solar flux based on the true progression. In other words, that's based on Kepler's second law. And the red is based on the mean progression. So the point here is that, you know, the simplifying or the simple analysis doesn't always work for you. Make sure you understand what the implications are. So if you were doing a thermal analysis on a spacecraft orbiting Mars, you probably want to, you know, understand, let's see, in this particular case, 600 watts per square meter versus 625 watts per square meter. You know, that's not necessarily a trivial percentage difference. You might want to go that extra mile and make sure you have the actual distance from Mars on the particular date of interest to factor into your analysis. And you can't always get away with the simplifying assumption. Okay, let's take a look at Kepler's third law. Then I think we'll be about done with this segment of the lesson here. Kepler's third law says the square of the period of orbit, t, of a planet is proportional to the cube of its mean distance, which is a, to the sun or its central body. So in other words, the period squared is proportional to the mean distance cubed. So if I take a look at the orbits that I have here, that's just saying that the outer orbit period is the cube root of 8 times the inner orbit period, because the outer orbit as a semi-major axis, that's twice that of the inner orbit. So let's look at the derivation. For this, we need to look at parameters of an ellipse in more detail, and I promised a little bit more detail on eccentricity. So you can see eccentricity here is just the distance from the center of the ellipse to one of the foci divided by just from the center of the ellipse to the edge of the ellipse, or C over A. There's a parameter P here. It's also called the semilattice rectum, and it's A times 1 minus E squared. And then there's some other relationships here that are important for an ellipse. So we start with the conservation of angular momentum. H is equal to R cross V. And remember that the magnitude of H is just given by R times V times the sine of the angle between them. Okay, so here's the angle R, here's the angle V, the angle between them. That's just the definition of cross product. But I can also define that in terms of another angle phi, and then I can expand upon it a little bit more and get that here. And I wanted to point out here that unfortunately the letter V and the letter nu look so similar to one another, but I need both of them in the derivation. This is the true anomaly. I'm measuring the angle from para-apsis, and I just want to point out that V represents velocity, and I used a different color for nu and nu dot here, which is the true anomaly. So I just didn't want people to get all of that confused. So the magnitude of the angular momentum becomes R squared d nu dt. You'll probably remember seeing this a few pages back when I used R squared d theta dt. Here I'm just using nu because I'm measuring it from para-apsis, but it's pretty much the same thing here, conservation of momentum. All I'm going to do is rearrange that equation so now that I can solve for dt. So dt in terms of R squared over h times d nu. And if I look at a differential area element in the ellipse, it's just given by 1/2 R squared d nu. So I can substitute that expression into my earlier relation. And now I have a relationship between dt and dA. It's just they're proportional by 2 over h. And if I integrate and I simplify, I arrive at a mathematical expression for Kepler's third law. So let me show you where I got this. I've got an expression for differential area of an ellipse, but I'm going to just short circuit right to the finish line because I know that the area of an ellipse is just pi times a times b, right? So when I put that in there, 2 over h times pi times a times b, that's equal to the period. I just integrated that. And then if you remember all of these expressions that I had a few pages back on 87, I do the appropriate substitutions in there, and I end up with this expression 2 pi times the square root of a cubed over mu. So let's step back from it and take a look at it. If I square that, I get the expression at the bottom. And remember, Kepler's third law states the square of the period t of a planet is proportional to the cube of its mean distance a to the sun or its central body. So period squared is proportional to this mean distance cubed. Okay, very nice, elegant law. So as long as the semi-major axis A is the same as the orbit period, there's going to be, the orbit periods are the same. Look at what I've got here. Both of these orbits have the same semi-major axis, but they have dramatically different eccentricity values. Yet look at what happens as these orbits are being calculated here. They both make it around the orbit the exact same amount of time. Watch the little gray ball go around there, and they both pass through their starting points at the same point. So we see that the orbital period is a function of only the mass of the central body and the semi-major axis. And we're going to use that in determining planet orbital periods using Kepler's third law. So we've got the Newton's constant of gravitation. We're going to use the sun as a central body. And what we're going to do is we're going to change out or use the semi-major axes for all of the planets and come up with an approximation for the orbit period. So when I do that, you get the values below. When you look up the actual precise orbit periods, they vary slightly. I want to say that these are like 99.9% of what the values are, but I believe there's other perturbations that are taken into account. But just based on Kepler's third law, you get extremely close for that. You get 1.00 for Earth's orbit of 1 year. You know, these are all based on Earth years. So just wanted to point that out, that you get very, very, very close calculation. But again, don't use these for mission planning purposes. So one other example here is a geostationary orbit, and it has a period of 24 hours and an orbit inclination of 0 degrees. So what you want to do with a geostationary orbit is you want to put a spacecraft over the equator so that it's staring down on the same portion of Earth all the time. And they're used for communication satellites and weather satellites. So when you look at the daily weather forecast on television and they show you the satellite photo, that's coming from a geostationary satellite that's out over the equator. Or if you have satellite TV at home, you notice you have antenna on top of your house, and we'll talk about that more in just a second here. But let's take a look at an example here. So I put together a model where a spacecraft is orbiting at a geostationary orbit, and hopefully you're able to see that the spacecraft is staying over the same point on the planet, but of course it's staying in the equatorial plane. So the example problem here is at what altitude d must the satellite be positioned to be geostationary? So we say that we have our equation for the orbit period using Kepler's third law, and we rearrange it so that we can solve for the semi-major axis. And once we solve for the semi-major axis, we can solve for the altitude by subtracting out the radius of the Earth. So it's just saying that the altitude for a geostationary orbit is about it's a little bit above 22,000 statute miles above the Earth. One really important thing here, I'll just share with you a common mistake that I've made at times, and I would just ask you to take note of it so you don't make the same mistake. A lot of times people get orbit altitude and orbit radius mixed up. So sometimes you may have the altitude of the spacecraft and you plug it into the orbit formula, or the period formula, and you'll get the wrong period. Remember that whatever you put in here has to be the orbit radius, which is from the center of the central body out to where the spacecraft is. So look at whether or not you have altitude or you have orbit radius and adjust it accordingly to make sure that you're using the right number of calculation. So I mentioned earlier that some of you may have satellite dish antennas on top of your house. And one of the things that you'll notice about them is that they stay fixed. They point at a constant point in the sky. They don't articulate. You've seen some satellite dish antennas at facilities that may track various spacecraft going across the sky, but a geostationary orbit is designed to stay at the same point in the sky. So that's why you don't need a motor drive in your antenna to stay focused on it or to stay pointed at it to get your television signal. One of the things I will point out is you can pretty much tell where you are on the planet by looking at the local dish antennas. In the lower left-hand photo, I took a picture at 29.5 degrees north latitude of a satellite TV dish pointing to a spacecraft up over the equator. And then I happened to be up near 60 degrees north latitude last summer, and you'll notice that the antennas are pointed much lower in the sky because at 60 degrees north latitude, a satellite up over the equator is going to appear much lower in the sky. So I would invite you to take notice of that on your world travels. The closer you are to the equator, the higher the antenna is going to point, and the closer you are to the poles, the lower the antenna is going to point. And then, of course, the azimuth is going to be dependent upon what longitude you're at and what satellite it's pointing at. So we're wrapping up part 2 now. I'll invite you to start submitting your questions. We introduced unperturbed two-body problem, and we derived the governing differential equation, and we showed that the unperturbed two-body problem obeys conservation of specific mechanical energy and conservation of specific angular momentum. And if you think about it, there's nothing dissipative in there. So that makes sense. In other words, it was just purely gravitational force. So there was really nothing to take energy out of the system. So it's really not a surprise that we're obeying specific mechanical energy or specific angular momentum. We also derived Kepler's 3 laws of planetary motion, and we applied the laws to problems of interest, at least I hope they are of interest to thermal engineers. So at this point, we're at about the halfway point in the course, and I want to take this opportunity to see if you have any questions, and then after that, we'll break for a short while and then resume with the remaining portion of the course. So I'm open to any questions that you have.
We do have one question
Okay.
from John Lockhart. He doesn't have his city or country, but he was asking, is it not possible to have a circular orbit in plane with an elliptical orbit?
Is it possible to have a circular orbit in the same plane as an elliptical orbit? I don't see any reason why there wouldn't be, but of course, what would happen is, let's say you set up a circular orbit and an elliptical orbit, where the elliptical orbit is in the same plane, but its para-apsis, its low point, was the same altitude as the circular orbit. So what would happen in that particular instance is you'd have a spacecraft going around the circular orbit at a constant rate, and you would have a spacecraft in an elliptical orbit, and since the ellipse would be bigger than the circle, it would go around. It would have a longer period. However, when the spacecraft got to close to the circular orbit altitude, it would be moving faster than when it would be moving towards its high point, or apoapsis. I'm not sure if I answered your question. I don't see any reason why you couldn't have them. I guess it would really depend on what you were trying to accomplish with the 2 orbits. Are there any other questions or comments?
None right now. I will give it another 20 or 30 seconds because the stream is just slightly behind.
Okay. That while we're giving people the opportunity to ask their questions, I guess what I would propose doing after we're done with the questions here is that we take, I was going to say, a 15-minute break. If people want to suggest a longer break, whatever works. I think we're doing really well time-wise here. You know, once we're finished with the questions here, we'll do a 15-minute break and come back and resume with the lesson. I saw, did another question flash up from the person who asked before? I want to make sure I answer.
It was a quick comment. They're saying thank you.
Okay.
There are some comments going on in the chat right now asking if the units of the solar flux calculation appear incorrect. They're wondering if you're missing something. And somebody else commented that 1,300 watts per meter squared is a lot less than they thought, since they said some ground solar panels can see 1,000 watts per meter squared. Do you have any comments?
1,371 watts per meter squared is very close, or is the accepted solar constant. Let me go back to that. So unless I'm missing something, I stand by that. I stand by that number. You'll see 1367 published or 1371, but units wise, this is in astronomical units. So this is at 1 astronomical unit, and so no, this should be correct. But if anybody has a specific correction they want to discuss, I'm certainly happy to discuss that with them.
There is another question from
Yes.
Emmanuel in Los Angeles. Can you describe the difference between the orbit altitude and orbit radius again? Just another clarification.
Certainly. Okay, let me go. That's an excellent question, and I'm glad we got a question about it, because it's very easy to make that mistake, which basically says, yes, I've made that mistake myself. So let's look at that. Okay, so the orbit radius is measured from the center of the central body out to where the spacecraft is at. Or in this case, you know, for circular orbit, that's the semi-major axis. Okay, these calculations that we're doing for period here are based on that. So if I were to put in the altitude, which is measured from the surface of the central body out to here, that would be incorrect. You just get the wrong answer. So the important thing is that the orbit cares about where it is with respect to the center of the body. So make sure what you're putting in there is the semi-major axis. The difference being the radius of the planet. If you look at it down here, we calculated the semi-major axis required for a 24-hour period, and then we subtracted off the radius of the planet to get the altitude that was posed in the question. I hope that answers the question.
Yeah. All right. I think I see another one.
Okay.
I think that was a good answer to that question personally. David said he finds it fascinating that Kepler came up with these solutions based only on observations, with Newton deriving them 100 years later. Has any increased mathematical understanding led to observations that were not known by Kepler?
So that's an excellent question, and when we get into part 4, which is advanced orbit concepts, I'm going to talk about a discovery that was predicted before it was actually observed, and that has to do with the Jupiter's Trojan asteroids. And to me, that was a triumph of orbital mechanics. So I'll save that story for that section. But if the person who asked the question is interested, there's a lot of good books out there
that talk about the history of orbital mechanics. I mentioned there's some good historical write-up in Bate, Euler, and White, but for example, I think the existence of the planet Neptune was kind of inferred by its effect on, I think it was Uranus, before Neptune was discovered. So I would just say there's a lot of interesting reading that can be done about that. I will touch on one example when we get to part 4, so I'll save it for then.
All right, another question, Carlos. When you cross multiplied R and V and equaled 0, would that imply that they are the same? You canceled them out when you did R prime cross R prime. Maybe mistake on the variables, but if we can go back to that section and clear it up a little bit.
Let's see. I want to make sure. Do you remember which section it was in the derivation?
May have to give them a sec. I believe it's farther back than it was. Fairly early on in the. Sorry.
And we're back at conservation of specific angular momentum. And then we're back at conservation of specific mechanical energy. I'm not sure we go back any further in derivations than this. But if the person asking the question can point us to a specific derivation, or if they want to look at it during the break, we can tackle it in another section. We answer questions.
He says, I think it was slide 46, so maybe one more slide.
Okay.
Back.
That's kind of the definitions. All that is expansion of terms. The radius vector r is just the magnitude r times the unit vector. Velocity is just the derivative of r, but just remember that it's not just a change in r dot. I mean, it's not just a change in dr dt. There's also a d theta dt term in that. And then the acceleration is just the derivative of the velocity, which is
You're not saying maybe slide 50, if we move forward, is because I do recall seeing the cross. There is a cross product where it's 0.
Okay. I'm happy to, if you want to take a look at it during the break, I need a few minutes break. I can come back and flip through slides. If they remember what it is, we can go to that. But what I propose doing is, unless there's any other questions, now we can tackle those other questions and then tackle this during the breaks, give everybody a little bit.
Yeah, we do have another question from Texas, League City, Texas. Can a TV dish located at the North or South Pole see its geostationary satellite? Would it be below the horizon?
Well, let's look at it this way: as if it were an infinite distance away, it would the antenna would be. It would be like right on the horizon. And one of the things I had to scratch my head about when I was looking at these antennas at high north latitudes is we have to remember that a geostationary satellite is a lot closer than at infinity. It's a little over 22,000 miles up there. So my guess is that you wouldn't be able to see it from the North Pole or the South Pole because it would probably be below the horizon. It certainly wouldn't be of much use to you, is what my guess is. Maybe somebody who knows more about it could educate me, but just based on geometry, I can't imagine it being of either visible or of much value.
And one more, just asking for a further explanation of the formula for the solar flux. Oh, if you go back one slide, I think I just saw the R cross V, but.
Okay, do you want to tackle that one first?
It's all right. We'll find it later for Ed.
Okay.
So let me go to the solar flux formula. I'm starting to regret not having put more of an expansion in here, but let me just draw a mental picture for you here. The sun is outputting a certain amount of energy every second.
And let's assume that it's a point source and it's blasting the same amount of energy out in all directions. Okay? If I were to construct a sphere around the sun at some distance, let's call it 1 astronomical unit distance, then the amount of energy that the sun is putting out, at steady state, the amount of energy the sun is putting out has to be equal to the amount of energy that's crossing that spherical surface at 1 astronomical unit. If you were to look at that sphere on a per square meter basis, every square meter of that sphere would have 1,371 watts crossing it. So the flux at 1 astronomical unit is 1,371 watts per square meter, okay? Now, let me draw another sphere around the sun at any distance, okay? Let's put it out at 2 astronomical units, okay? If I look at the total amount of energy crossing that sphere or any sphere, it has to be the same. It's conservation of energy. Okay? But at 2 astronomical units, that surface area is 4 times that of the sphere at 1 astronomical unit. So at 2 astronomical units, the solar flux crossing that sphere is only 1/4 of that crossing it at 1 astronomical unit. So this formula, and like I said, I clearly stated that you have to do it in astronomical units. When I put in a 1 for, the denominator, 1 squared, and that just says at 1 astronomical unit, I have 1,371 watts per square meter. If I put in 2 astronomical units, or a 2, then 1,371 divided by 2 squared, divided by 4, I get 1/4 the flux. If I go out 40 astronomical units to like Pluto, I think it's somewhere out around 40 astronomical units away, that denominator goes to 1,600, 40 squared is 1,600, then the solar flux that you get out at that distance is just pitifully small, okay? So you can see it in here. I didn't put Pluto in here. Much as I'd like to keep it as a planet, it isn't. So if you look out at Neptune, the solar flux is just so small out at Neptune, less than 2 watts per square meter. So I hope that's a little bit more of a clear explanation for the person who asked the question. Is there another question, or did somebody find the slide that they want to go to for the cross product?
One more interesting question. Anna from Sergipe, Brazil, probably butchered that, is a freshman and interested in studying this area and was wondering if it'd be too early to begin studying it now, or what kind of advice you would give for somebody just starting out.
Oh, well, first of all, heat transfer is fascinating, and orbital mechanics is fascinating as well. I would say, you can study some things on your own. You can take the short courses like this, but if you have a chance to take an elective in your studies that gives you an opportunity to study orbital mechanics, that's probably a great way to start if it isn't part of your curriculum. But I'm very glad you're interested in it. And good luck with your studies. Are there any more questions?
There's one in our chat. It's going to be kind of hard for me to describe it because it's asking about a formula.
Okay. Well, if you start going through the formula, I might be able to find it.
Yeah, it says, what can you say about JS is equal to P over 4 multiplied by pi multiplied by d squared?
Can you read the equation again?
Yeah, has JS equal to P over 4 multiplied by pi multiplied by d squared. There's no.
I don't recall that equation in here. if the
And they said P is the total power output from the sun.
Oh, yeah, that's right. Yes, and he's asking what more can be said about that.
Yes.
So I want to make sure I understand the question. When I was explaining moments back the
solar flux, like I said, the sun, if you want to look at what the output of the sun is, you could add up all of the flux that crosses the 1 astronomical unit line, or the 1 astronomical unit sphere. Like I said, the same amount of energy that's being emitted by the sun has to cross that sphere that's 1 astronomical unit from the sun. So if you calculated the area of that sphere, which would be 4 pi r squared, and you'd want to do that in like meters, so 4 pi r squared, and you multiplied it by 1,371 watts per square meter, you'd get an approximation of how much energy the sun is outputting. I've not done that calculation by hand, but it would be a very easy thing to do. Any other questions?
Nothing left I can see, and this would probably be a good break because 15 minutes would put us right at about 11 a.m. Central. I want to go back and find the one cross product to look over, but then I think for everybody else, we can be on a
Okay. Maybe we can save that question for the next question period, but I'm fine with that. So it's about a quarter of the hour, so we'll start out at the top of the hour again.
Sounds good.
Okay.
Okay, so I understand that we're back now. I hope everybody had a good break. And if you'll recall before the break, I think there was a question about some cross products, and I think we were able to figure out where the question came from. So let me offer a 1-minute digression back to that. This all came about with respect to our derivation for conservation of angular momentum. And maybe the colors mixed up or caused some confusion, but let me just walk you through it again very quickly. We have our governing differential equation, r double dot plus mu over r cubed r is equal to 0. And what we did for this derivation is we're saying we're going to cross that with r. So we have r cross the first term, r cross the second term, and by the way, r cross 0 is just 0, so I left it as 0 vector. Okay, and the first thing we notice here is this second term, r cross something times the vector r. R cross r is a vector cross with itself, so it's 0. So this goes away. We're left with r cross r double dot down here is equal to 0. So now we're going to take a look at r cross r double dot in a little more detail because it's actually disguised as something else. And I mentioned that somebody who was very smart in math, and I'm very grateful to her or him for coming up with the original derivation, recognized that this r cross r double dot is actually part of a larger term. It's actually part of d dt of r cross r dot, and that's equal to, when you expand that derivative, it's r dot cross r dot plus this term that we like. Well, even though things look more complex, they actually get a lot simpler because r dot cross r dot here, the second term, or this term right here, a vector cross with itself is 0. So now we can say that this term that we like is equal to d dt of r cross r dot. So now we go back to our original equation, and we're left with d dt of r cross r dot is equal to 0. So this is something, a derivative of something is equal to 0. So if I integrate it with respect to time, I get r cross r dot is equal to a constant. Well, r cross r dot is r cross v, which is the angular momentum, specific angular momentum. So we have r cross v is equal to a constant. Voila, we have conserved specific angular momentum. So I hope that helps clarify it for the person who asked the question. And if this wasn't the question that you asked, go ahead and resubmit it. Please take note of the page numbers, and we'll try to tackle it at the end of section 3. So I'm going to go move on to section 3 now. Let me jump ahead to section 3. Okay, and we're going to talk about perturbed orbits now. So the world would be great if everything obeyed the two-body problem without perturbations, because as you saw, we've got some nice pure results in there that led us to some direct calculation. But the universe isn't so simple. There's cases where we account for some other forces acting on the orbit or perturbations. And we're going to actually focus on a couple of them that arise from a non-spherical Earth. We're going to show how this gives rise to some effects that we can actually exploit to give us the desired orbit, but it also explains some things that we as thermal engineers really care about. For example, like beta angle and the variation in beta angle over time. So we'll take a look at some useful things you can do with these orbits. Of course, the implications for thermal engineers. So let's revisit our governing differential equation. This has been a really good starting point for us. When we derived the two-body problem under the influence of only the gravity, we got this nice expression at the top, and the right-hand side of our differential equation was 0 because there weren't any perturbing forces. As I mentioned, some interesting things happen when there's a perturbing force, so that our differential equation now becomes familiar left-hand side, but the right-hand side is not equal to 0. There's many forces that can perturb an orbit. We're going to talk a little bit about the spherical harmonics, one of them in particular. But you just think about it this way, when you go up into orbit, it's not an absolute perfect vacuum. There's little bits of atmosphere there, and as you get closer to the Earth, there's more and more atmosphere. So over time, that's going to drain energy from an orbit, and it's going to lower the orbit to the point eventually where it comes crashing back through the atmosphere. There's radiation pressure. The sun
the sun, the photons hitting the spacecraft, that's going to affect it over time. There's other celestial bodies, even though we're far away from Jupiter, it's tugging away at our spacecraft in orbit. There's tidal forces. The moon lifts up some portion of the ocean higher, that shifts where the mass is in the Earth, and that affects the orbit. And then there's things like mass concentrations, and those are very famous on the moon. If you look at the lower right-hand picture on the screen there, there's a map of lunar gravity anomalies as measured by NASA's Grail mission. And one of the things I remembered when I was putting a course together is that low lunar orbits aren't real stable for long periods of time, because all of these mass concentrations make the moon deviate from being a perfect sphere with mass effectively at the center of that sphere, and long-term stability of lunar orbits just doesn't happen. So that's something that's really, really important as well. The picture on the upper right-hand portion is actually a representation of the non-spherical Earth, and we're going to be focusing our efforts on a non-spherical Earth here. If you look at the scale on the right-hand side, what you're seeing here is the measurement of the Earth radius. So if you look at around the equator, you'll notice that it's a little bit more orangish yellow, which means that the Earth is slightly more or it has a slight equatorial bulge as compared with the poles. So up near the poles, maybe the Earth radius there is like 6,360 some odd kilometers, but at the equatorial it's like 6,370 something. Okay, and that causes a slight equatorial bulge, or that's evidence of a slight equatorial bulge. And it means that Earth isn't, the mass distribution of the Earth isn't that of a perfect sphere. So we're going to have to find some way to deal with that. And that actually causes some interesting effects. So we're going to focus on two perturbations in this lesson, both of them arising from the non-spherical shape of the Earth. We're going to look at precession of the ascending node. So if you remember where the ascending node of the orbit is, that's the point where the orbit crosses from south to north, crosses the equatorial plane going from south to north. It turns out that the perturbations we're going to study causes the ascending node to move westward for orbits where the inclination is less than 90 degrees, and eastward for orbits where the inclination is greater than 90 degrees, or we'll call those retrograde orbits. The other perturbation we're going to study is the precession of the para-apsis. That's the low point in the orbit. Moves in the direction of the orbiting spacecraft for inclinations up to about 63.4 degrees, and in the direction opposite the orbiting spacecraft for inclinations above this value. Now, both of these effects have some interesting consequences that we're going to see how mission designers can exploit those to their benefit. So we're going to focus on the non-spherical Earth. And like I said, Earth is not a perfect sphere. And what you do to handle that mathematically, and I'm talking about like terms on the right-hand side of that differential equation, is you can actually express the gravitational potential as a summation of many terms that is representative of the actual gravitational potential. And these terms are called harmonics, and they have associated coefficient, J with a subscript, and that's a subscript that multiplies a Legendre polynomial. And you determine these J values through experimental observations. We're going to be focusing on a harmonic called J2, the J2 term. And if you look at the numbering on the harmonics, the even number harmonics are symmetric about the equator. The odd numbered harmonics are anti-symmetric. And we're going to look at, or we're going to talk about things called zonal harmonics, sectorial harmonics, and tesseract harmonics. So a zonal harmonic, you can see that in the lower left picture there. Those are, function of latitude. The sectorial harmonics depend only on the longitude, and the tesseract harmonics depend on both the latitude and the longitude. So think of it this way. If we had a perfectly spherical Earth, we wouldn't need to worry about any of this stuff. But we need some mathematical machinery to give us a way of approximating the effects, or the effects on the gravitational potential that arise from things like a non-spherical Earth. So if I have an extra band of mass, or effectively an extra band of mass in the equatorial region, then I might want to address that with a zonal harmonic. So it turns out we're going to be looking at the J2 zonal harmonic, or the oblateness perturbation. I at least wanted to show you that there's other terms there. And I remember going through the derivation of this in grad school, and all I can remember is that it took about 15 pages of math to derive it. So I'm not going to try to relive that here. Earth is not a perfect sphere. It's oblate, has that slight bulge in the equatorial region, and it gives rise to these orbit perturbations that we're going to talk about here. So the precession of the ascending node, the rate at which it precesses is given by this equation that you have here on the right. And then the precession of the periapsis is given by this equation here. We're going to look at these in a little bit more detail. Notice the parameter n at the bottom is just 2 pi over the period, and the value of J2 is given as 1.082, et cetera, times 10 to the minus 3 for Earth. That's dimensionless. I will point out that I think in other lessons that I've given in the past, I remember the first time I learned about J2, I saw the parameter expressed with the negative sign in front of it. I've since seen it, and it may have been my error all along, but I've since seen it as a positive value, and that that carries the negative into the equation, et cetera. But I just wanted to point that out. So based on what I'm seeing, the J2 value is listed as a positive number. So let's first take a look at the oblateness perturbation. If you watch the animation at the right, what you're going to see is that on successive orbits, the ascending node of the orbit is going to move to the west for orbits that are inclined less than 90 degrees. It turns out when you incline the orbit greater than 90 degrees, the precession is eastward. And like I said, we're going to use that to our advantage here. But this is the equation, and we're going to go ahead and do a little bit of work with it here now. So the orbit that really exploits this is called a sun-synchronous orbit, and those are useful for Earth observation because the orbit's designed to pass over sunlit portions at pretty much the same local solar time. That if you want consistent illumination for ground targets and things like that, then the sun-synchronous orbit is the right thing for you. I will draw a distinction that the sun-synchronous orbit is not the same as a geosynchronous orbit. A geosynchronous orbit has an orbit period that is a function of the rate that the Earth rotates. So a geosynchronous orbit, most famously a geostationary orbit, would have one orbit every 24 hours. This has a much shorter orbiter period, and it is not the same as a geosynchronous orbit. So if we want to achieve this orbit, the ascending node of the orbit's got to maintain a consistent offset from the orbit subsolar point. In other words, you'd like the geometry to stay as fixed with respect to the sun as you can possibly make it. You want to move the ascending node of the orbit at the same rate the sun appears to move around the celestial sphere. And if you were to stand out in space and you were to look at Earth, over the span of the year, the sun would make one circuit of the Earth, and we'll talk about this more in a little while here, it would make one circuit of the Earth in a year. And if you were to look at the Earth and hold the Earth as a fixed coordinate system, the sun would be moving eastward. So what we would need to do is make the ascending node of our orbit also move eastward. But if you remember what I mentioned before, is that for orbits that are inclined less than 90 degrees, the precession of the ascending node is westward. So what we need to do is we need to make the precession of the ascending node eastward, and we need to make it move at a rate that is as close as we can make it to the way the sun is moving. So let's take a look at this equation. We've got a few parameters that we can wiggle right here. So let's focus on a circular orbit. So let's set eccentricity to 0. So that kind of drops out of the equation here. And the parameters that we have to mess with here are the inclination of the orbit, I, and also the semi-major axis. So what I'm telling you here is that a sun-synchronous orbit is actually a family of orbits. It's the combination of the parameters inclination and the semi-major axis that give you the ascending node angular rate that is in the same direction of and the same magnitude of the average motion of the sun around the celestial sphere. So you can look it up, but there's a number of combinations available. One of the combinations is if I incline the orbit 98.2 degrees with respect to the equator, so it's slightly retrograde, and if I select a semi-major axis of 7,083, so note someone asked earlier the difference between the altitude and the semi-major axis. The distance of this orbit from the center of the Earth is 7,083 kilometers, but its altitude above the Earth's surface is only 705 kilometers. So again, it's very important to draw that distinction there. I'm specifying semi-major axis. And what that will do is that will give me an ascending node angular rate of 0.986 degrees per day. And then most importantly, it will be moving eastward. So that means the precession is going to go around the Earth the same rate as the average motion of the sun. Okay. Let's take a look at precession of the periapsis. The oblateness perturbation, that's that same J2 term, if you notice it in here, also causes the periapsis and the apoapsis to precess at the rate that's expressed here. The precession is positive when this term 4 minus 5 sine squared I is greater than 0, and it's negative when 4 minus 5 sine squared I is less than 0. So if we can find out when or at what inclination this precession goes to 0, then we have a way of locking the periapsis and the apoapsis of the orbit in space. And we can use that to our advantage as well. So the example we offer here is the Molniya orbit, and that's used by the Russians. So just a little bit of background, if you have communication satellites in geostationary orbit over the equator, they're not of much use to people living at high latitude. So if the Russians used it, remember much of Russia is at high latitudes, because as someone asked earlier, these communication satellites would appear very, very, very low in the sky. So what you'd like to have is a satellite that orbits at a higher inclination, because if you're at a ground station at a high latitude, you'd love to have your satellite high in the sky so you could more easily point your ground antenna to it. The problem is the only place you can make it stay fixed at a fixed point in the sky is if you put it over the equator. So what you can do instead is you can come up with a highly elliptical orbit and lock the apoapsis and periapsis in place, so that while the spacecraft may not stay at the same point in the sky, it'll spend long periods of time at that same point in the sky. And if you have a number of different satellites in a constellation, when one of the Molniya satellites falls back to Earth, falls back toward Earth on its elliptical orbit, another one would be going out and spending a long time almost stationary in the sky. So let's take a look at this. We want to lock the location of the apoapsis and periapsis. We want to find out where the rate of movement of the periapsis goes to 0. So you can diddle with some of these other terms. Well, you can't diddle with these other terms. You can't make the semi-major axis infinite. You can't do all of that other stuff. But what you can diddle with is the inclination. And if you look at this 4 minus 5 sine squared I term, here we want to find out when that goes to 0. And when we solve for the inclination there, that's true when the inclination is about 63.4 degrees. So if we put a spacecraft in an orbit that's inclined 63.4 degrees, you see what happens here is the red dots represent periods of time that are 10 minutes apart. You can see that the spacecraft, when it gets low to Earth, it whips around the Earth and doesn't spend much time at a low altitude. But then as it gets closer and closer to periapsis, it slows down. And you notice all of this period of time out here where the spacecraft is just lingering in the sky. It's not stationary, but it's close to stationary. And so you've got the elliptical orbit that keeps it out that far, but most importantly, you've inclined it at an inclination where you've locked periapsis and apoapsis in place. So the periapsis always stays here, and the apoapsis always stays here. So that means you will always keep that orbit at a high inclination in the northern hemisphere. Okay, so what are the effect of the orbit perturbations on the thermal environment? Precession of that ascending node changes the angle at which the sunlight falls onto the orbit plane. And if you work in the thermal world, you'll know that that's referred to as the beta angle. So as that beta angle changes, an orbiting spacecraft is going to experience a variety of thermal effects. It's one parameter that affects how much environmental heating a spacecraft surface experiences. We'll talk about that. But it also affects how much time a spacecraft spends in eclipse. So we're going to take a look at both of those. If you want a concise definition that you can use at a cocktail party for beta angle, you can just say that beta angle is defined as the angle between the solar vector, which is a vector that points from the center of the Earth to where the sun is, and its projection onto the orbit plane. So here we have the orbit plane right here. And we have a vector that's pointing to the sun wherever it might be throughout the year. And if I look at that vector projected onto the orbit plane, and then I take the angle between them, that's what the beta angle is. Okay? So before we go into the derivations anymore, we need to establish a coordinate system, because the key to all of this, and actually the key to the attitude transformation, is that we're going to define a number of vectors that are going to be useful to us. And then what we're going to do is we're going to measure angles between them. And it's really, really, really important for us to define all of these vectors to be within the same coordinate system. So what we're going to talk about here is something called the celestial inertial coordinate system. We'll revisit this when we get to attitudes. And the way this celestial coordinate system is set up is, imagine the origin being at the center of the Earth. And then the easiest one to do here is, let's fire a z-axis from the center of the Earth up straight to Earth's north pole. That's the z-axis. The x-axis takes a little bit more explanation, but let's fire the x-axis from the center of the Earth out through Earth's equator, and I want to point to the location in space where the sun crosses from the southern hemisphere to the northern hemisphere, and that would be on the first day of northern spring. That's called the vernal equinox. Okay? And I'm going to mark that point in space, and I'm going to say that my x-axis is in that direction. So I've got my z-axis and my x-axis. If I go z cross x, that gives me y. And I've got my right-handed orthogonal system. And that's the coordinate system for which we're going to define all of these vectors. Matter of fact, it's going to be the coordinate system that we seek to define all of our vectors and do all of our transformations in when we get to attitudes, because it makes things a lot easier. You'll see why. So the first thing we're going to do is we're going to come up with an expression for where the sun is. And we're going to use our celestial inertial coordinate system. And you can see it, the center of the Earth is the origin. You can see the x-axis coming out and pointing to the point in space called the vernal equinox. You can see the z-axis going out the north pole of the Earth. And if we hold this coordinate system to be our inertial coordinate system, if we were to hold that inertial and go out into space and look, we'd actually see the sun making its path around that celestial coordinate system. And as you know, Earth's axis is tilted about a little less than 23.5 degrees with respect to its orbit around the sun. So that means the sun is going to orbit in a plane that's tilted 23.45 degrees with respect to Earth's equator. So let's do a little check here. If I were to put the sun at the vernal equinox on the first day of spring, that's the place at which the sun is crossing from the southern hemisphere to that's the first day of northern autumn, or also called the autumnal equinox. And then 3 months later, the sun is at its southernmost point, or it's what we call the summer solstice, the winter solstice, because it's winter in the northern hemisphere. So right now, I need to come up with an expression that says, on any given day of the year, where is the sun within this plane, or on this pattern within this plane, and that plane is called the ecliptic plane. And again, this is all defined with respect to the celestial coordinate system. So I said the apparent motion of the sun is constrained to the ecliptic plane, and it's really governed by two parameters. One of them we talked about already. It's the tilt of that plane with respect to Earth's equator. That's called the obliquity of the ecliptic, and right now it's presently about 23.5 degrees, and it's not going to change appreciably within our lifetime. The other one that we haven't talked about yet is a parameter called ecliptic true solar longitude. And that changes with date, because on this path, the sun will make one circuit around this coordinate system once a year. So that means gamma has to go from 0 to 360 degrees over a 365.25 day year. So we're going to go back and do our Euler angle transformations now, because what we want to do is we want to come up with a vector, an equation that tells us where, that points to the sun on any given day of the year. So we're going to use our two Euler angle rotations, starting with our celestial inertial coordinate system. And what I'm going to do is I'm going to start with a vector that is the sun pointing to the vernal equinox. And then the first thing I'm going to do is I'm going to rotate that entire plane an amount 23.45 degrees, equal to the obliquity of the ecliptic. So I'm orienting the path of the sun as it should be with respect to the celestial inertial coordinate system. And then once I've got that, any motion of that vector S is constrained to that ecliptic plane. And what I'm going to do is I'm going to do a rotation of gamma, uppercase gamma, or called the ecliptic true solar longitude, about that new z-axis. So that's visually what we're doing here. So mathematically, the transformation is this. The first thing I want to do is an x-axis transformation by an amount epsilon. And then I want to do a z-axis transformation about our new z-axis that's transformed. And I want to transform the vector 1, 0, 0, which is the vector that was pointing along the x-axis to the vernal equinox. And when I do that, I've got an expression for the solar vector that tells me, well, first of all, we'll assume this constant, but on any given date, this is a vector that points to where the sun is. So that is our first vector in the celestial inertial coordinate system. I want to do the same thing now with a vector describing the orientation of the orbit. So in that same celestial inertial coordinate system, we're going to define another unit vector called O, which is the orbit normal vector, which is a vector that points normal to the orbit plane. So remember, when we talk about planes, it's always best to describe them as a vector that's pointing normal to that plane. Again, in the celestial inertial coordinate system. So to orient that orbit plane, we need two parameters. One of them is the orbit inclination, which is the amount that orbit is tilted with respect to the Earth's equator and celestial equator. And we also need to know the right ascension of the ascending node, which is a measure of the angle between the x-axis of the celestial inertial coordinate system and the point where the orbit crosses the equatorial plane going from south to north. So let's take a look at this. You can see some angle omega here. Here's the vernal equinox, and here's the point at which our orbit goes from the southern hemisphere to the northern hemisphere. So what we're going to do is we're going to do a couple of transformations that orient this plane, more importantly, orient this vector with respect to the coordinate system. So we can form the orbit normal vector by two Euler angle transformations. First, we've got to do a rotation of the unit vector about vector of right ascension the ascending node. And then so once we fix that ascending node, then we're going to tilt the orbit up inclination I about the new x-axis. So if this is our orbit plane here, like I said, it's useful to define a vector that's normal to the orbit. So you're going to see this, instead of this being 1, 0, 0, this is going to be a vector 0, 0, 1, because right now it's pointing purely in the z direction. So right now this is the untransformed system. Then we do our first rotation about the z-axis, and you see I kind of spin this plate here. That moves the right ascension out over here. And then the second rotation is a rotation about the new x-axis, because we want to rotate about this. And you notice how that orients the orbit normal vector the way that we want. And again, it always stays perpendicular to the orbit. So the transformation is, again, we do a transformation about the z-axis by an amount omega. Then we do an Euler angle transformation about the new x-axis by an amount I. And we transform the vector 0, 0, 1 because it was pointing up along the z-axis. Voila, we have an orbit normal vector, again, defined with respect to our celestial inertial coordinate system. Okay, so if we want to calculate the angle between the vector S and a plane, you really have to determine the angle between the vector and the vector normal to the plane. Okay, so we ultimately want to know the angle between vector and the plane, but like I said, it's easier to take the angle between the two vectors. So look at what I've got here. I've got the orbit normal vector up here, and I've got the solar vector here. I'm going to look for this angle phi. And by the way, I can relate phi and beta, because if I just subtract pi over 2 from phi, then I have beta. So right now, let's focus on getting phi, and then we'll end up with beta. You can see that the angle between these two vectors, the orbit normal vector and the solar vector, I can get the cosine of that angle by taking the dot product of those two unit vectors. So we have an expression for the orbit normal vector, and I transpose that vector and the solar vector here. And when I do that, I've got this expression here, taking the dot product. And then since beta is just phi minus pi over 2, I can come up with my expression for beta. And it's the arc sine of this, all of these parameters here. So look at what this is. The beta angle is a function of inclination. It's a function of the obliquity of the ecliptic. It's a function of the ecliptic true solar longitude. And it's a function of the right ascension of the ascending node. Now, let me make things a little bit simpler for you here. Within our lifetime, the obliquity of the ecliptic isn't really going to change, so epsilon is essentially constant. For the orbits that we deal with, I think mostly we assume that they're constant, so we'll say the inclination is constant for the purposes of this discussion. So there's two parameters here that change over time. Gamma, as we saw, goes from 0 to 360 over the span of a year. And the right ascension of the ascending node, as we saw from the perturbations that we did before, changes dependent upon the J2 zonal harmonic, and that's going to be and that's going to have it's going to change with, or I should say, omega will change with inclination and eccentricity and the semi-major axis, etc. So we've got two of these four parameters here that are going to change as a function of time. Turns out, for things like low Earth orbits, the gamma is kind of a long-term variation, and omega tends to be a short-term variation. So I just want to point that out when you see some graphs coming up here. The other thing I wanted to point out is beta is physically limited by the plus or minus the obliquity ecliptic plus the absolute value of the inclination. However, I'm going to point out, even though it's physically limited in there, it doesn't have to experience that. And you'll see that when we get to the sun synchronous orbit. Just because it's kind of geometrically bounded by that, you can do some tuning to the orbit so that, like for a sun synchronous, where it never really sees that inclination. So anyhow, that's the limits of the beta angles. I will also point out there's a convention where you have beta angles where the sun is north of the orbit plane. Those are considered positive beta angles. And when you have beta angles where the sun is south of the orbit, those are considered negative. That's the convention that's used. So here's a typical, or I'll say a representative profile. If I have a 408 kilometer altitude orbit, a circular orbit with an inclination of 51.6, which is kind of what the space station flies, you can see what happens over time. This is one of many possible profiles. In reality, the beta angle is going to be limited. If you think of a band, it goes like this on the upper end, and a band that goes like this on the lower end here, then the beta angle, the profiles you get are going to be bounded by those bands. But what you see here is a long-term variation, and this is due to Earth's motion around the sun. And then the short-term variation is due to the precession of the ascending node. So I call it a roller coaster. I'm sure nobody else does, but I kind of call that the typical beta roller coaster. And you can see what happens here when you get, there'll be periods of time when you're at low beta, and there'll be periods of time when you're at high beta. And those are going to have an effect on how much time you spend in Earth's shadow, but it's also going to affect on what sides of the spacecraft the sun is impinging. And we'll talk about that in a little bit more detail. So I got ahead of myself a little bit here. As beta changes, there's really two consequences of interest to thermal engineers. It's the time that you spend in eclipse, and that's going to vary, and the intensity and direction of the heating incident on spacecraft. So we'll take a look at those now. Let's take a look at some shadow geometry. We'll talk about the umbra and the penumbra. The umbral region is the shadow where the sunlight is completely obscured, and the penumbral region is where the sunlight is partially obscured. And the way I like to explain this, and this picture is not to scale, but we can explain this with lines of sight. If I were to draw a line from the edge of the Earth to where the sun is, to the edge of the sun, extend that out in the other direction, I've got this line. Same thing happens if I do it on the other end. Now I'm going to draw two more lines. I want to draw a line that's tangent to the Earth here, but goes to the opposite limb of the sun. And then I'm going to do the same thing here. It goes to the opposite limb of the sun. And I'm going to extend those lines out into space. Now imagine that I'm an astronaut free floating out in space. If I'm up here where my cursor is at, I am not blocked by any portion of the Earth. And as a matter of fact, if I were floating at that location out in the white area here, I would be able to see both limbs of the sun, which means there's no obscuration, and that I would be feeling the full intensity of the solar flux at that distance from the sun. If, however, I start moving into the gray region here, the penumbra, let's look at what happens. When I'm in here, I can still see part of the sun, but I'm blocked from another part of the sun here. So that means I'm going to still see some sunlight, but it's going to be diminished. It's not going to be the full intensity because I'm experiencing some blockage from the Earth. Finally, when I move into this region called the umbra here, the lines of sight show me that I can see neither limb of the sun, which means I'm completely blocked. The Earth's completely blocking me, and I'm not getting any sunlight on me. I mentioned this diagram's not to scale. You know, in reality, I think Earth's umbral cone goes out something like around 800, or the apex of it is something like around 800,000 miles from Earth. And that makes sense because if any of you like to go out and watch eclipses, you know that there's some times where the moon falls into Earth's umbral shadow, and we get a total lunar eclipse there. And then there's other times where it's only slightly obscured, and we get into the penumbral eclipse. So if you think about what happens during a total lunar eclipse, the moon first moves into the penumbra, then it moves into the umbra, then it moves out into the penumbra, and then back into full illumination. And the moon is only about 230 or 240,000 miles away. So as I mentioned, the umbral cone extends far beyond that. If you're in low Earth orbit, it doesn't take long to go from penumbra to umbra. So here's a photo taken, a sequence of photos taken during a space shuttle mission, and you can see what happens as the Earth, as the sun is setting or rising behind the Earth. You can see the intensity of the sunlight gets diminished and diminished and diminished. Well, for low Earth orbit, that happens very quickly. That happens like on the order of seconds. It's not minutes or hours that happens. So we might be able to make some simplifying approximations here that give us an opportunity to simplify our analysis. Excuse me one second. So if the time in the penumbra is minimal, in other words, if you can neglect it, and as a thermal analyst, it's up to you to determine that. If you've got something that responds very, very quickly to changes in environmental heating, then you may not be able to neglect it, but for most hardware, maybe you can. You can simplify it by coming up with a cylindrical shadow assumption. So here's what I did. I attempted to make a representative sketch of what the umbral cone looks like in the region close to Earth. And the good news is the angle was so shallow that I had to exaggerate it by a factor of 4 so that you were able to see it. So the black dashed line represents the cylindrical shadow assumption, and the blue line represents the conical assumption, where the apex is perhaps 800,000 or so miles out in space. And what it shows me is even for orbits that are, you know, pretty high up, but still close to Earth, you know, if you can neglect the time that you're spending in penumbra, a cylindrical shadow assumption is really a pretty good approximation. So what's good about the cylindrical shadow assumption is it simplifies some calculations that we're going to make on how to calculate how much time we're spending in eclipse. And to do that, I'm going to generate a new coordinate system here. So this is not the celestial inertial coordinate system that I was showing you before. I'm going to define a new coordinate system. I'm going to use a beta subscript on it just to remind us that it's a different coordinate subsystem, where I'm going to say in this coordinate system, the sun is always in the XY plane of this coordinate system. And the orbit is inclined some angle beta with respect to the sun. So here's the sun over here. It's always going to lie in the XY plane. Y is, Y is going into the page here. We're going to take a look at it from another direction in just a second here. And I'm going to incline my orbit beta. Now this does not defy our definition of beta, because here's the solar vector coming from here going to the sun. And if I project that solar vector onto the orbit plane, my definition of beta here is still consistent with the formal definition of beta that I gave you previously. The other things that we're going to need here is we need to know the radius of the Earth or the radius of the planet, so I'll call that R sub E. And then here's our cylindrical shadow assumption here. So for the rest of this derivation, let's go look down on this orbit from above here. And right now I'm gonna tilt this orbit back so that it'll be in the XY plane so that we'll be able to take a look at it. So looking down onto the orbit plane gives us this geometry. I've gone back to a beta equals 0, so that way the orbit is in the XY plane. The sun is still in the XY plane. And of course, when I rotate about this, then I still have the same cylindrical shadow if it's going to be opposite the sun. And I'm going to define some other parameters here. Okay, we've got the radius of the Earth, the radius of the planet here, r sub e. We've got h, which is the altitude of the orbit. I'm going to do this for a circular orbit. We've got a vector r that points from the center of the Earth out to where the spacecraft is at. And then I'm going to use this other, I'm going to define this other vector here called r prime, which will be very important in our derivation. Because what it does is I'm going to take the vector r and I'm going to project it onto the YZ plane. So Z is out of the page. I'm going to project this vector r onto the YZ page because the length of r prime is going to be used to help us determine when we're within eclipse. The angle theta is measured from the subsolar point, and that's going to tell us where our spacecraft is with respect to the orbit. What we're looking for is an expression for r prime, which is a projection of r, as I said, onto the YZ plane in our coordinate system here. Okay? Notice that when the magnitude of our r prime vector is less than the radius of the planet or radius of Earth, the spacecraft is in umbral shadow. Okay? So whenever r prime gets to be less than this dark circle here, that means we are in umbral shadow. So that's going to be our indicator that we're in eclipse. The spacecraft position vector, you can express it as a function of altitude above the planet and the planet radius, and then the angle from orbit and the beta angle. So this vector r, the magnitude of r is just the radius of the planet plus the altitude. And then I've just done the trigonometry here that tells us what the ij and k values are, and it's going to be a function of orbit angle, and it's going to be a function of the beta angle. And then the projection of that vector onto the YZ plane in our beta coordinate system is just the y and the z coordinates of that. So you notice this guy goes away, and it's just a function of these two things here. Okay, so that's going to be the magnitude of our r prime vector. So got that here. I can just give you the. I'm sorry. That is our r prime vector. The magnitude of it is just by Pythagorean theorem, just the square root of the squares of the sum of the sides. So the onset of the shadowing occurs when the magnitude of r prime is less than re, and that's the condition that's shown at the bottom here. So you can see it's a function, or the angle at which we enter is just a function of beta, and it's a function of altitude, right? It's a function of h, and it's a function of beta, because the radius of the planet is fixed. So now that we know the theta of the eclipse, it's really a simple matter to determine the entire eclipse period, and I'm going to do it for a circular orbit, because the total angle shadowed is just twice, excuse me, it's just, we're in sunlight for twice of theta, so 2 times pi minus theta is going to be the amount of time that we spend in eclipse. And if you do that, the fraction of the orbit spent in the sunlight eclipse for a circular orbit is clearly related to beta. So all I needed to do was solve this equation for theta, and then I recognize that 2 times pi minus theta is the eclipse period, and since I know the orbit, or since I know the period for a circular orbit, 2 times pi minus theta divided by 2 pi is the fraction of this time spent in eclipse. And if I multiply that by the orbit period, it tells me how much time I spend in eclipse. So I've done that for that 408 kilometer, 220 nautical mile circular orbit. And you can see the fraction of time spent in sunlight, and you can see the fraction of time spent in eclipse. Now, what's really interesting about this is that for a wide range of betas, maybe up to about beta of 30 to 40, the change in beta has very, very little effect on the fraction of time that you spend in sunlight or the fraction of time that you spend in eclipse. But as you get higher and higher beta, you get closer to a point where you kind of fall off of a cliff. And for a 408 kilometer orbit, by the time you get up to it's right around 70 or 70.5 degrees beta, you're getting to a point where you're spending 100% of your orbit in sunlight and 0% of your time spent in eclipse. So I'll just point this out. We talk about it a little bit later. I think I have a graph that shows it later. But imagine you're an astronaut flying on the space station, and for long periods of time, I'll go back to the picture here. For long periods of time, you're flying at low betas, and then sometimes you get in excursions up into higher betas here, where you just come up and get very close to the beta above 70 degrees. So what you're experiencing here is relatively constant day-night time. And then as you get closer to here, you get to a point where your orbit is spending less and less time in shadow. And there's 2 periods during the year where you may not pass into Earth's shadow for perhaps 5 days at a time. And then very quickly after that, your beta changes and you get back down into a range where you're experiencing regular day-night cycles. So that's just a very, very interesting phenomenon. And it's important for your spacecraft. It's important for your spacecraft because you may get periods of time where you're not going to be getting the relief that you need on surfaces that are pointing to the sun when you're in a 100% sunlit orbit. Of course, right now we rely on passing into Earth's shadow to give us some relief from the heating of the sun. So let's look at an example. Geostationary orbits, they have an orbit inclination of 0 because we put them over the equator. And if the orbit inclination is 0, the limits of beta are going to be plus or minus 23.45. So if you imagine, there'll be times when the sun is at the northernmost point and the sun will be at the southernmost point. So the maximum angle to the orbit plane for an orbit that's inclined 0 is going to be plus or minus 23.45. So what we expect to see is only a seasonal variation in beta, and you only see a seasonal variation in spacecraft eclipse. So if you've worked on geostationary spacecraft, you may hear them talking about eclipse seasons. So what I did here is I did the calculation. On top, that's just basically the solar declination, but it's also the beta angle here, and I ran it out for a whole year, and you can see how the beta angle changes. And look at what happens here when we use even when we use the cylindrical shadow assumption. I think I got numbers that are like dead on or within the same day as those published for eclipse seasons for geostationary spacecraft. So what happens is much of the year you spend in 100% sunlight, but there's periods of time where the solar declination is such that you get eclipse seasons, and during the orbits, you might only spend as much as 95% of your time in the sunlight, with the remaining amount of time spent in eclipse. And that happens 2 times a year. This is a close-up. I did some screenshots from thermal test. I didn't use it for the calculations, but if you want to see what the geometry is like, in each of these pictures, the sun is out here, whatever, and you can see when the sun is out there, and what you can see is there's periods of time where the orbit passes through Earth's umbral shadow. There's periods of time where it's below the shadow. There's periods of time where it's above the shadow, where you don't get any. Here's the example I was talking about before with the space station orbit. This is the same representative profile that I showed before, but if you want to take a look at the time spent in eclipse, all I did here was calculate the beta angle, and then for the beta angle and the altitude, I calculated the entry and exit angle, and then for a circular orbit, I knew the angular span of the time spent in shadow, and the angular span spent in sunlight, and I looked at that as a fraction of the overall orbit period. As I mentioned, for a wide range of beta angles, you really don't get much variation in the time spent in sunlight, but then as you get towards your higher beta angles, higher extremes, look at what happens. You go through a rapid variation or rapid change in the fraction of time you spend in sunlight, to the point where you get a number of days, a couple of times a year, where you're not spending any time in the eclipse. Let's take a look at another example, sun synchronous orbit. They're designed, as I mentioned, that the orbit ascending node moves in the same direction and at the same average rate as the sun's motion about the ecliptic plane. You can accomplish that by selecting the right combination of altitude and inclination. And what I'm going to do here is show you the case for 705 kilometers altitude. That's not the rate. That's not the orbit radius or the semi-major axis. That's altitude above the ground, and 98.2 degrees inclination. And I don't know if this particular set of circumstances is used for any particular spacecraft at the moment, but what I wanted to point out, just in terms of the characteristics of the orbit, is look how flat the beta angle profile is. I mentioned before what the limits of the beta angle physically could be, But if you've tuned your orbit so that the beta doesn't vary much for the sun synchronous orbit, I've got a situation here where the beta is about minus 7.5 degrees and doesn't get any more than about maybe minus 12 or minus 13. So that's a very narrow beta angle range compared to, say, plus or minus 75 that we had for this other orbit here. What's really interesting is, again, for the low beta angles, the time you spend in sunlight, it's really not that sensitive to it. So look at how flat time we're spending in sunlight is, which basically tells me that to the degree possible, we are holding the orbit orientation as close as we can to the movement of the sun. And remember, the sun is moving around the celestial sphere. We're getting the orbit to move around precess around the celestial sphere as close as we can to the same rate that the sun is moving. And then I thought, for fun, let's just see how well tuned this orbit is. So I did a what if. On the left-hand side, I have the same data for the 98.2 degree, 705 kilometer orbit. And then I just said, well, let's see how well tuned this is. Let me just change the inclination to 99.0 degrees on the right and 705 kilometer orbit. And look at what happens to the beta angle. Look at what happens to the time spent in sunlight. You're still not getting a whole lot of variation in the time spent in sunlight, but notice how the character of the curve changes. Look at the beta angle profile. We went from about minus 7 or so degrees beta to about plus 25 or so degrees beta. So when I said that the sun synchronous orbit is really tuned, I really mean it. Look how beautiful that is. You're using nature and orbital parameters to give you a really flat beta angle versus time and time spent in sunlight profile. Just thought it's an interesting example here. I want to talk a little bit about beta angle on flux on incident on spacecraft surfaces. Imagine the situation where you have something like a space station orbit, and as you saw, the beta angle is going to vary from large negative values to large positive values. And in this particular example, you can see, let's say the red curve there, surface 5 is getting illuminated by the sun each orbit, and surface 6 is not getting illuminated by any sun. Later on in the year, on the black orbit, you can see 5 and 6 are edge onto the sun. Neither of them are getting it. And then later on, surface 6 is getting illuminated, but surface 5 isn't. So it's really important to know, to understand how the beta angle varies and understand the attitude orientation of your spacecraft, because seasonally, or not just seasonally, but just because of the precession of the orbit or the progression of the orbit, it's going to have an effect on what kind of fluxes you're getting. And it's not just solar fluxes, because as you get up to higher betas, you're going to get less albedo flux, things like that. So there's a lot of movement going on here. And fortunately, our analytical tools are able to handle those things easily. But this is why it's necessary to look at many different beta angle cases to determine what your worst cases are for each portion of the spacecraft. So we're at the end of part 3 now. Just as a reminder, we consider the effect of perturbations arising from Earth's oblateness. So we understand precession of the orbit ascending node and precession of the para-apsis. And you can exploit those perturbations to create some useful orbits such as sun synchronous and Molniya. And then we looked at the effect of perturbations on beta angle and the consequences for the spacecraft eclipse, and just other consequences for heating on the spacecraft. So at this point, let me ask and see if there are any other questions, and we'll take a break for questions here and then proceed on to parts 4 and 5.
All right, it looks like our first question is from Praveen in India and asked if you can explain a little bit more on slide 142. I believe that was with the eclipse season.
Yeah, first of all, thank you for the slide numbers. Was there something specific, or do you want me to just re-explain it? I'm assuming, was there a specific question on that or just general explanation?
I think a general explanation, especially of the eclipse season.
Okay, so to do this, I'm going to go back a little bit further and walk you through the process again. So for a geostationary orbit, we've got the radius of the Earth, we've got the altitude for geostationary, and you notice the other thing in here is we have beta as a parameter. So if I know what beta is on any given date, I can plug that in here along with the other nodes and calculate the angle at which I enter eclipse. Once I know the angle that I enter eclipse, I can use this geometry to look at, this is the fraction of the orbit that I spend in eclipse. So 2 times pi minus theta divided by 2 pi is just my fraction of time in eclipse. 1 minus that is my time in sunlight. So now I can go to the geostationary orbit. This is the beta angle profile because it's just the movement of the sun because the orbit stays within the equatorial plane. So I can plug in beta and I can plug in, the altitudes, which stay constant. And I can calculate that I'm in 100% sunlight at this location. And as beta changes, there's going to be a period of time in which I start intersecting the planet's shadow. And if I were to follow that through time, on this particular date here, I would be spending about 95.5% of my time in sunlight, the rest of it in eclipse. And then as that eclipse season ends, I go back to spending 100% of my time in sunlight until I get to the next eclipse season. And if I want to look at it closer, this is what the geometry looks like. The sun is shining in this way, so it's below, the orbit is below the shadow. Here it's passing through the shadow, and here it's above the shadow. So that gives us rise to full illumination, different levels of blockage or different levels of eclipsing, and then we're back into 100% sunlight. So I hope that clarifies it for you. Is there another question?
Yes, Jerry Vera from Dallas, Texas asked, does the beta angle return to 0 every year on the same date?
Excellent question. No, it doesn't. And the reason for that, the reason for that is because while the sun may repeat once a year, the rate at which the ascending node precesses does not have to repeat after exactly 1 year. It's going to be dependent upon the inclination and the altitude and the eccentricity of the orbit. So that's an excellent question, and the short answer is no, it doesn't have to return to beta equals 0 on the same date each year. For the geostationary orbit, let me go to the geostationary orbit, that's kind of a special case because the orbit is always in the equatorial plane, so the only parameter that's really varying is the sun. So that one's going to repeat each year just because it's kind of a simplified geometry. Is there another question?
Yes. Again, from Jerry from Dallas, Texas asked, are the nadir and zenith heat fluxes identical for both the positive and negative beta angles?
The nadir and zenith facing. Okay, so
heat fluxes.
Right. Yeah. So excellent question for positive. The answer is no, but it may not be for the reason that you think it is, and that is for Earth's orbit around the sun. When we're at high negative betas, that tends to be a period of time when the sun is in the southern hemisphere, which means we're closer to the sun at that point. So the fluxes are higher because Earth is closer to the sun than when we're at high positive beta, when we're further from the sun. If we were at the same distance from the sun the entire year, then the zenith-facing solar fluxes would be the same for positive or negative betas. For the same positive or negative beta, and the nadirs would be for the same positive and negative beta. But because we're at a different distance from the sun, it's different. Is there another question?
Yeah, you're getting that in. Jason from Pittsburgh, Pennsylvania asked, he said, generally speaking, I found that the lowest beta angle where the spacecraft does not go into shadow gives the largest total integrated heat flux on the spacecraft over the orbit. Are there any circumstances where that wouldn't be true?
So it's an excellent question. I'd have to think about it. And I'm thinking about a paper I wrote some years back where the highest beta angle where it does not go into shadow did give me the highest fluxes for a simplified geometry. The reason I'm a little hesitant to state that what you're saying is fully applicable is it's really going to be spacecraft dependent. If the spacecraft is just a cube, then maybe what you're saying is correct. But if there's other things, and this depends on optical properties and the geometry and the orientation of the spacecraft,
you may have to study it in a little bit more depth before you can make that claim. But I would be cautious about making that a general statement. Any other questions?
We can keep going, and very interested in this topic. Punit from India says, will the subsolar point be the same throughout the orbital period, or will it change with respect to time?
So the subsolar point, okay, so excellent question. The subsolar point, everything's moving up in the orbit. So the short answer would be no, and the reason why I say that is you've got the orbit, the ascending node precessing, and you have the sun moving around the celestial sphere. So from one orbit to the next, like in a low Earth orbit, it may not change appreciably. It may change just a small amount. Over the span of a day, the sun's going to move about a degree, and then the orbit ascending node is going to move in the opposite direction, and it's going to be dependent upon the inclination. So it really depends on what you're trying to do, but as a general answer is technically, no, it does not stay the same. Another question?
I think one more question in chat, going back to the nadir and zenith, where you show the surfaces. They asked, will the design material be the same for surface 2 like it is for surface 5 and 6, because it's normally in a more shadow-like region?
So excellent question, but it really depends upon what you want your spacecraft to do. Let's look at it this way. Surface 5 is going to see more sun,
more direct sun than surface 2. And it really depends upon what your spacecraft is designed to do. If you're designing surface 5 to be a radiating surface, you'd want to put like a low alpha, high epsilon type surface on there. So it's really hard to make. I really can't make a general statement about it, because it's really dependent upon what your spacecraft shape is like and what you want it to do. So I'm sorry, I can't offer any more guidance on that. I didn't know if there's any other questions. I just want to make sure we've got 56 more slides to go through and a little bit less than an hour to go. And I want to make sure that we have time to cover that. I didn't know if there were any more questions now, or if we could proceed on to part 4.
That was the last of the questions for this section, so I think we can proceed.
Okay, very good. And I'm hoping we'll have time for more questions or discussion. So the next one here is we're pretty much done with our discussion or detailed discussion of orbits, but I wanted to show you, just to give you an appreciation for how fantastic orbital mechanics is, just a brief 50,000 foot overview of a number of different orbit situations, just to give you an idea of how complex things can get. So we're going to talk about a transfer orbit and an orbit plane change. We'll actually do a little calculation or two on those. And then I'm just going to kind of tell you about aerobraking orbits, gravity-assisted orbits, restricted three-body problem, halo orbits, the orbit for Artemis 1, and the gateway orbit. So let's take a look at those. So let's talk about a transfer orbit. A transfer orbit is used to raise a spacecraft orbit after launch. They're also used for interplanetary trajectories. So when the Mars Perseverance rover was launched a couple weeks back, they had to put it on a transfer orbit that's let it intersect with Mars or arrive at Mars. I think it's February 18th of 2021. And the way you change an orbit is you change the energy of the orbit. And there's not a lot of different types of transfer orbits, but the one I'm going to show you here is called a minimum energy orbit that's going to be required to attain a desired orbit transfer. And that's called a Hohmann transfer or Hohmann ellipse. So our challenge here is we desire an interplanetary trajectory, and we want to go from planet 1, which is shown at departure down at the bottom here, to planet 2, which is shown at arrival. Okay, and for the sake of the simplicity of the calculation, we're going to assume that these are both in the same plane, and we're going to assume that they're both circular orbits. So we're making life a little simpler on ourselves. So the lowest energy transfer occurs when the speed change, delta V, is the lowest, and also that it ends up taking the longest because you're going the slowest. But for circular orbits, planet 1 is traveling at velocity v1, And for planet 2, it's traveling at velocity v2, okay? And some other things on the geometry, the radius, or, I'll say the radius, which is the semi-major axis for orbit 1 is r1. The radius for orbit 2 is r2, okay? So if we want to transfer, we need to ensure the extent of our new orbit reaches from one planet to the other. If I create a transfer trajectory that doesn't make it all the way out to planet 2, then I haven't done my job. So what I've done here is I've actually constructed a half of an ellipse, and the half of the ellipse has a perihelion, or the closest point to the sun, at planet 1, and its furthest point from the sun is at planet 2. And since I've constructed an ellipse here, you can see if I look at R1 plus R2, that's the major axis of the ellipse. So half of that is the semi-major axis, and that's just R1 plus R2 over 2. So that'll be the semi-major axis of our transfer orbit. So the subscript T is for our transfer orbit. So the total specific energy of the orbit is just the sum of the specific kinetic energy and the specific gravitational potential energy, right? Conservation of energy, and we showed that was constant. We also know from our earlier study of the two-body problem that the specific angular momentum is also constant, right? So we're going to leverage stuff that we've learned before. So since h is constant, we can calculate it at any convenient point in the orbit, right? Because it's the same, it's constant everywhere. So I'm going to say, let's consider it at paraapsis. So this is basically going to be the velocity at Earth and, or I'm sorry, velocity at planet 1, departure, and the velocity of planet 1 and the radius of planet 1. And recall earlier that the paraapsis is just a times 1 minus e, okay? And if you want to prove that to yourself, take the equation that we had for the general conic and put in the true anomaly of 0, and you'll see that the equation reduces to a times 1 minus e. So that's like for Earth, semi-major axis is 1 astronomical unit, eccentricity is 0.0167, so 1 minus 0.0167 times 1 astronomical unit is Earth's perihelion distance, okay? Also remember from earlier, h squared over mu is equal to this, and that if you want to refresh or go back and take a look at when we came up with the general equation for a conic. So all I'm going to do is, move some terms around there. Okay, so we've got that. Now, repeat the expression for total specific mechanical energy. And what I want to do is I want to obtain or substitute the expressions obtained for the momentum at paraapsis. So you notice the radius at paraapsis is a times 1 minus e, so I put that there. Right? And the angular momentum is just h sub p squared, I square it there, okay? And when you do the math on all of this, out pops another expression for the specific mechanical energy, which we didn't talk about before. It's just minus mu over 2 times the semi-major axis. So that, the semi-major axis remains constant. Mu is just g times the mass of the central body. That remains constant. So we've confirmed to ourselves again that the specific mechanical energy remains constant. So we're going to use this minus mu over 2a. I'm going to do is I'm going to set minus mu over 2a equal to our other expression for specific mechanical energy, and I'm going to do some rearrangement. And I'm going to solve for v. So I'm going to form an expression for the velocity v. So what this tells me is at any given point in the orbit, if I know what distance it is from the central body, and I know the semi-major axis of the orbit, I can tell you what the velocity is at that particular point in the orbit. Really handy equation. Okay. So at planet 1, we're already traveling at the circular orbit velocity. So all I'm doing is I'm plugging R1 in here, and this is also R1 because because that's the radius of the orbit. When I plug that in there, 2 over R1 minus 1 over 1, I just get mu over R1, and that tells me what the velocity is of planet 1 going around the sun. But we need to be traveling at the transfer speed that puts us on that elliptical path from planet 1 to planet 2. So the transfer orbit is the semi-major axis is R1 plus R2 over 2. And I want to find out what the velocity needs to be at R1 for that. And when I do that calculation, I end up with this over here. Okay. So the delta V is, this is the velocity that I need to be transferring at. This is the velocity that I'm traveling, because the spacecraft will initially have the velocity of the planet around the sun. The difference between those is the delta V. So I just subtract one expression from the other, and I end up with this. Okay. So what this tells me is how much extra kick, how much extra velocity I need to give to the spacecraft, or the burn that I need to do, how much velocity I need to add to the spacecraft to get from planet 1 to planet 2 along that minimum energy ellipse. And the time it takes to travel from planet 1 to planet 2, well, you saw it was just 1/2 of the entire elliptical orbit period. So 1/2 of, let's use Kepler's third law, the transfer orbit semi-major axis cubed divided by mu, so that's equal to this here. So if I know that the semi-major axis for planet 1 and planet 2, I can calculate what the time of the transfer orbit is. So that's just a useful calculation to give you an appreciation. Not all interplanetary transfers are minimum energy. So if you tried to do the math here, I think the Perseverance rover is going to Mars in less than 9 months. So that means it would be using something other than a minimum energy trajectory. Now let's take a look at the plane change. A plane change is used to change the inclination of a spacecraft's orbit. So you consider this diagram here. Let's say we're currently in, we're going to consider both of these circular orbits just to make our life easier. But let's say we're currently in the green orbit, and associated velocity that we're traveling at is V, green V. And we want to change the spacecraft to the orbit, the circular red orbit, and its associated plane. And the difference in the inclination between the orbit planes is an angle theta. And note here, since the orbits will be at the same altitude, we're assuming that the velocity V is, or the speed V is equal to the magnitudes of both the green V and the red V vectors. So if you take a look, closely at the vector equation here, we can see we've got the green orbit there that is currently traveling in that velocity, but we want to change it to the red velocity. And to change the trajectory from the green velocity to the red velocity, we need a change in the velocity by delta V. Okay? And when we do that calculation, the magnitude of delta V is just equal to 2V times the sine of theta over 2. Now, the thing I wanted to point out here is that you don't see a whole lot of orbit plane changes going on, because it's a very, very, very expensive maneuver from a propulsion standpoint. I didn't have an opportunity to look it up for this, but my recollection is that the space shuttle, back when it was flying, was only capable of about a 2-degree plane change. Otherwise, it would have just been so expensive from a propellant standpoint. But this is the math behind it that tells you the delta V that you would need to change the plane. The rest of the orbits I'm going to talk about here just kind of at a very high level. Aerobraking is a technique used to reduce the amount of fuel required to slow down a spacecraft. So the way you do that is by progressively skimming through the atmosphere on successive orbits. And of course, you're invoking drag there to slow down the orbit. And when you invoke the drag, then it lowers the apoapsis of the orbit. So this is the Mars Global Surveyor aerobrake baseline profile. I'll show you how long it took to lower the orbits down to an orbit that the Global Surveyor could work on. So that's aerobraking orbits. Gravity assist orbits, you use those by redirecting an orbit by making a close passage to another planet. So this is an example of the Juno spacecraft, which is now at Jupiter. It was launched from Earth on August 5th, 2011. It went around the sun once and then made another pass by Earth on October 9th. And what it does is, by making those passes, it injects additional energy into the spacecraft. It actually robs energy from the planet. But it's such a minuscule, small amount, Earth would never know it, but you use these so that you can give enough energy to reach the spacecraft. There's some spacecraft that have multiple flybys of planets. I've seen, I forget which spacecraft it was, but there was a Venus, Earth, Jupiter gravity assist. I want to say that was for Cassini, but I won't swear to it. But it involved multiple gravity assists, and just to give you real appreciation for the sophistication behind some of this mission design and orbit design. The restricted three-body problem is really, really interesting. If you have two large masses, M1 and M2, and they're orbiting one another, there's regions in space that can serve as gravitational nodes where spacecraft or other celestial bodies can collect or be placed. Those are called Lagrange points. Actually, to be technical, there's 5 points. There's 3 of them that are collinear, L1, L2, and L3. And I think those are called Euler points. And then L4 and L5, I think, are the ones that are actually only called Lagrange points. But this can be in any two-body system. So think of Sun, Earth, or Earth, Moon. I'll try to give you some examples for either here. If you look at L1, L2, and L3, those are unstable. L4 and L5 are stable. And I will tell you, I took a graduate course in this. Actually, it was the first graduate course I took in orbital mechanics before I took fundamentals of astrodynamics or perturbation methods. So I took three-body astrodynamics first. And it's absolutely fascinating because it's a one-parameter problem. Everything's just a function of the mass ratio of the two bodies that are involved. The third body, like a spacecraft or an asteroid or whatever, those are considered to be massless. And when you solve for that, you can get these Lagrange points. And as I mentioned, L1, L2, and L3 are stable, but you can still use them. I'll show you how they're used. L4 and L5 are stable, which means if you put something there, I guess it'll either orbit it or stay very, very close to L4 and L5. And what's really interesting about that, someone asked a question earlier about some of the insights from orbital mechanics. Joseph Louis Lagrange, developed the math for the Lagrange points, and he believed that asteroids might be trapped near the L4 and L5 points of the Sun-Jupiter system because those are stable. And it turns out that people started looking, and the first confirmed observation of a Jupiter Trojan asteroid was made by Max Wolf in 1906. So here's something that is predicted by theory, later confirmed by observation. And this is a animation of the L4 and L5 swarms. You can see Jupiter in the middle there, but the L4 and L5 points are in here, and there's a bunch of asteroids orbiting them. As a matter of fact, the Lucy mission, which is going to launch in a little over a year, is actually going to go visit Trojan asteroids in the L4 and L5 swarms. It's going to take about 11 years, and it's going to visit a number of asteroids in both swarms. So the Lagrange points are also used for spacecraft. When they launch the James Webb Space Telescope, it's going to be located at the Sun-Earth L2 point. And that's going to be way out past the moon here, but obviously you want to put it at a place where the sunshade is going to protect the optics of the spacecraft from the sun. But there's you can put it at the Sun-Earth L2 point. The Discover spacecraft, which was a video from the animation that I showed at the very beginning of the presentation today, is located at the Earth-Sun L1 point. So think of the Discover spacecraft right here, and that puts it in a really good vantage point to look down on the illuminated side of Earth, and it just so happened to capture a picture of the moon transiting here. So those are some really useful things that you can do with that. Halo orbits have been studied for a long time. I mentioned you can have any two-body system. So here's the Earth-Moon system, and the Earth-Moon L2 point is out past the moon, and they studied putting relay satellites there because you can have a spacecraft orbit the Earth-Moon L2 point, and it would be in constant view of the Earth, and it would also be in constant view with the lunar far side. So that would be a good communications link between Earth and the lunar far side. And then just winding things down here, give you an appreciation for how sophisticated things can get. This is the current plan for flying the Artemis 1 spacecraft, which is the first uncrewed Orion spacecraft. And it will get into something called a distant retrograde orbit and do burns to get back to Earth, and just giving an appreciation that not everything can be solved as the unperturbed two-body problem. And then finally with Gateway, Gateway is an outpost that's going to be used as a staging point to go down to the lunar surface, and just a little information here about what the benefits are of the type of orbit that Gateway is going to be in. So let's wrap up part 4 here and see if you have any questions. We looked at some advanced orbit concepts. You just recognize that transfer orbits are useful for changing from one orbit to another, like interplanetary trajectory missions or raising the orbit of something that's in Earth orbit. An orbit plane chain can be used to change the inclination of an orbit, but it's very, very expensive from a propellant standpoint. Aerobraking orbits, you can use it to lower an orbit by passes through the atmosphere using drag to remove energy from the orbit. Gravity assists, you can use those to employ on interplanetary missions to impart additional energy to the spacecraft. So it enables some missions that you might not otherwise be able to do with the propulsion capability that you currently have available. We looked at the restricted three-body problem. It explains the existence of asteroids at the Lagrange points. The solutions to the three-body problem, they're useful for placing spacecraft such as the Webb telescope. Talked about halo orbits you can use them for communications with the lunar far side, and then just giving you appreciation for the complexity of the orbits and sophistication of the orbits used for Artemis and for the Gateway mission. That's all I had in part 4. Are there any questions before we move on to the final part today? And if there are any straggler questions from part 3, I'm happy to try to answer those as well. I think we'll have sufficient time to finish up.
There is one question. I think we're waiting a little expansion on it, but Naman was asking if the spacecraft will be at the same position on aerobraking.
If the spacecraft will be at the same position. So I'm not sure I understand the question, but let me see if I can try to explain it again. If you lower the orbit to the point where the spacecraft is passing through the upper reaches of the planetary atmosphere, the drag is going to slow the spacecraft down. It's also going to heat it. You want to have to make sure that it's designed thermally to accommodate that. And it will lower, it will take energy out of the apoapsis of the orbit. I think what you do once you get down to the orbit that you want is you probably do some kind of burn to raise the paraapsis so that you're no longer passing through the atmosphere, but I don't know what the specifics are on that. Other than that, I'm not quite sure if I answered your question. Maybe you could type a little bit more about it, and we'll see if we can answer that while we look at some other questions.
In the meantime, we do have a question from Caitlin in Huntsville, Alabama, and asking if you can explain a little bit about what's required to keep an object in one of the unstable Lagrange points.
Gosh, I wish I could give you more information. What I learned when I was studying orbital mechanics in graduate school is, when you hear that they're unstable, you obviously think, well, that's not good. But I heard that it does not take a whole lot of energy to keep something orbiting there. Beyond that, I'm probably out of my wheelhouse on ability to clarify any of that. So I'm sorry, I don't have more information.
And Abby in Houston asked if you can explain a little bit more about how the near rectilinear halo orbit works and why it's a good choice for Gateway.
I am not the right person to answer that question. So I would have to go chase that down a little bit more. I don't want to give you a wrong answer, so I'd rather say that I'd have to look into.
I will say we had a short course yesterday on some of that on near rectilinear halo orbits, so maybe look into that next week. Not to distract from your course, but there was a lot of detail in it.
Well, I would point out, thank you. I would point out that this slide actually does give some information. It gives you easy access from Earth, gives you deep space environment, it gives you vantage point for observations, it's good for communications, and it's good for surface operations. So I think the reason why I'm hesitant to offer much guidance on that is it looks like this is a function of many things and not just purely two-body or three-body astrodynamics. But hopefully this slide can give you enough information, and I'm sorry I don't have more information on that.
Pranav from India asked, while changing orbit for V1 to V1 at angle theta, will that change be an instantaneous occurrence? Okay, so I'm assuming they're asking about.
Are they asking about the plane? Are they asking about the the plane change?
Yes.
The short answer is burns aren't instantaneous. So this is an idealized view of things. Burns usually take place over the span of minutes or whatever. So I think the short answer would be no. I don't believe that. I don't think the change is instantaneous because the burn isn't instantaneous. I think this is an idealization of just to kind of demonstrate what the physics is.
And Alyssa from Denver, Colorado asked if any satellites use the L4, L5 nodes in Earth's orbit, or could this be beneficial? So
that's an excellent question. And actually the very first place that I heard about the Lagrange points, and I didn't even know it at the time, there was a society years back, I think called the L5 Society, that wanted to put a space station or colony at I think it was the Earth Moon L5 point. So for the purpose of the discussion, assume this is Earth and assume this is the moon. And so I think they wanted to put a colony here. Are there any that use that right now? I'm not aware of any. I'd have to go take a look at it. Any other questions?
giving it one more moment. I think we've answered everything
Yeah,
so far.
I would offer that this be the last question because I've got one more section to go and we've got about 30 minutes to finish up.
I would say you're good to go for part 5. So we can.
Okay. All right. And hopefully we'll have an opportunity for a few more questions when we get there. So we've spent a lot of time talking about orbital mechanics, but I promised a discussion of spacecraft attitudes as well. And we're going to look at, to talk about attitudes, we really need to talk about reference frames. So we're going to look at 2 reference frames. One of them called local vertical, local horizontal. The other one's called celestial inertial. And we're going to look at attitude transformation strategy. And the good news is we've already worked out the math for that. We're going to use our good old Euler angles. What these transformations are going to do are going to orient the spacecraft surfaces with respect to solar and the albedo and planetary heating sources. And we're going to spend some time showing how to calculate, just a brief amount of time showing how to calculate the view factor. And we're going to tie it together with an example. Okay? So the attitude in concert with the orbit is really important to thermal engineers because you really need to know all of that to determine the thermal environment and what surfaces see what particular heating sources. So, the orbit's used to determine the distance from the sun and the magnitude of the solar flux. That affects the albedo and planetary heating components. So if you go to my introduction to on-orbit thermal environments, you'll see we do heat balances on the Earth and use that to calculate what the planetary heating fluxes are, et cetera. And then the evolution of the orbit over time affects the periods of spacecraft eclipse and orbit beta angle. So all of that is important to thermal engineers. The attitude is required because we want to determine where on the spacecraft to apply this environment. So to do this, we need the reference frames again. And just a spoiler alert, what we aim to do is we aim to define vectors and transform those vectors all into the same coordinate system. Because once we have those vectors in the same coordinate system, it's very easy to measure the angles between them. Once we know the angles between them, we can do some interesting calculations. Okay. So we start out with what a reference frame is. And think of a reference frame as a basis or a starting point for a subsequent series of rotations. So any axis of the coordinate system that's going to be transformed, it's aligned with the principal axis of the reference frame coordinate system at the beginning. In other words, when we start out, all of the axes of our spacecraft or whatever we're trying to do, everything is aligned with the reference frame. No rotations have taken place. So let's look at an Euler rotation sequence. The rotations need to be referenced to some starting point, and we'll call that the reference frame. So at the left, we've got some coordinate system called, we'll just call it a reference frame for now, Cartesian, ijk. If I were to do Roman rotation around the x-axis, you notice I've spun it around the I-axis, I'll call that I prime. That rotates j up into j prime, k over into k prime. That's one rotation. And then if I do another rotation,
that other rotation is about that new axis, I prime, J prime, K prime. So now we're going to do a rotation around the J prime axis. We get J double prime, which is aligned with J prime. We get K double prime and I double prime. Okay, so I just want you to see that's kind of the maneuvering that we're going to be doing here. So if we want to transform a spacecraft within a reference frame, we got to establish a meaningful coordinate system. So whatever project you're working on, there's going to be some coordinate system that's used for mission planning or for structural, whatever. So what I'm showing you here is what we're called the body axes for the space shuttle orbiter. And I want to point out that these are different than what the structural axes are. So if any of you worked on the space shuttle, you'll know a lot of the locations on the space shuttle were referenced with respect to the structural axis. But when we talk about attitudes, we're talking about the body axis. So in this particular instance, the plus X of the body axis is pointed out the nose, the plus Z is pointed out of the bottom, and the plus Y is pointed out of the starboard side wing. And you'll notice there's names associated with the rotations about these. When we roll about the X axis, we do a roll. When we rotate about the Z axis, we do a yaw. And when we rotate about the Y axis, we do a pitch. Okay. Just as another example here, there's the space station, International Space Station coordinate system. Again, X comes out I call it the front of the space station. That's probably meaningless though. And the roll is about that axis. The Y axis, the Z axis is the yaw axis, and the plus Y axis is the pitch axis. And just for reference, that plus Y direction is what's called the starboard side on the space station. Of course, the other side is the port side. So let's talk about how we define local vertical, local horizontal, and also a celestial inertial reference frame. If you look at local vertical, local horizontal, the X and L plane is the instantaneous orbit plane at the time of interest. Okay, so look at X and look at Z. Those are lying in the plane, in the orbit plane. Okay, and then the Y axis is normal to the orbit plane. Z always points towards the center of the planet, and the X point creates the right-hand system, and it's positive in the direction of motion. Okay. We define a celestial inertial system. You actually saw this before. You actually saw this graphic before. What we're doing here is we're saying that the center of the Earth is the start of the coordinate, or is the origin of the coordinate system. Z goes up to the North Pole. X goes through the equator and points at the location in space where the sun crosses the equator going from south to north. That's called the vernal equinox. Okay. And just a spoiler alert, regardless of what reference frame we're working in, whether it's local vertical, local horizontal, or celestial inertial, our ultimate goal is to transform everything into this celestial inertial system. And the reason for this, and the reason why I say we're going to do that even with local vertical, local horizontal, is you ultimately need to get all the vectors in the same system as where the sun is defined. And we define the sun in this coordinate system. So by transforming everything into the celestial inertial coordinate system, makes it really easy for us to determine between the angle between the sun and the spacecraft, or any of the other things, because we're working everything in the same system. So if you're making note of anything, just remember our goal is to transform everything into the celestial inertial system. Let's do a comparison. I did a screenshot again from Thermal Desktop. So on the left-hand side, well, first of all, in both images, the plus x-axis is red, the plus y-axis is green, and the plus z-axis is blue on the items in orbit. So on the left, I have the reference position, in other words, no rotations for the local vertical, local horizontal system, and I have the positions marked for the celestial inertial coordinate system on the right. So you'll notice that they're different. You know, for example, on the left-hand side, the z-axis is always pointing towards the center of the Earth, whereas in the celestial inertial coordinate system on the right, the z-axis is always pointing north. So you notice it's inertial with respect to the stars, whereas the LVLH coordinate system, think of it as kind of inertial with respect to the Earth. If you're looking up from the center of the Earth, you'll always see the same side of the spacecraft. So our strategy is to transform the surface normals. In other words, if we have a spacecraft and the spacecraft is composed of surfaces, those surfaces will have surface normals. And if I want to create a matrix or a vector of surface normals or a matrix of surface normals, what we want to do is we want to transform it in the same coordinate system for the unit vectors describing the location of the sun and the planet. Okay. Once all the vectors are transformed, the angles between the vectors of interest can be calculated. And once we know that, we know the view factors of the sun and the planet. And then from that, you'll see that we're going to get our heating. Most convenient to transform all surface normal vectors into the celestial inertial coordinate system. Okay. So let's transform attitudes in celestial inertial. If a spacecraft is flying in the celestial inertial reference frame, then the unit vectors representing the surface normals are transformed. So where you see where it says untransformed vector, and you'll see this in the example that we do. But let's say we've got a spacecraft surface that's facing the X direction on a spacecraft. So in the spacecraft coordinate system, that would be 1, 0, 0. It would have an X coordinate of 1, a Y coordinate of 0, a Z coordinate of 0. And what that means is it's a unit vector pointing out the X direction. If I transform that through pitch, yaw, and roll, or whatever Euler sequence I want, I get my transform vector in the celestial inertial system. Okay. Let's see. Okay, let's see. Now, if I want to transform local vertical, local horizontal into celestial inertial, it's a more involved transformation. First of all, you can recognize the last 4 items there, the untransformed vectors and the pitch, yaw, and roll. But look at all of this other stuff that we have on top of it here. In addition to transforming the orientation of the spacecraft and the surface normals, we've got to take it through its orbit parameters and transform all of the orbit parameters out of it so we can express this in terms of the celestial inertial system. So look at all of the stuff that we have to do. We have to transform it in right ascension, in inclination, and argument of paraapsis, and true anomaly. Then we've got to go through a reference change matrix, which I'll describe in a second. And then we'll do a pitch, yaw, and a roll transformation. The good news, again, is this is just our good old 3x3 matrix transformation. So even though it looks nasty and involved here, it's an extraordinarily easy thing to do in a spreadsheet or in some other computer program. So I would say if you want to experiment with this, do not shy away from it. I think you'll really enjoy working with this stuff. So what about the reference change matrix? Well, if you remember when we were back here, we had the reference positions for LVLH and celestial inertial were different. Okay, so we need some means of relating them or flipping one set of axes into another, and that has to be part of our transformation sequence. So the reference change matrix is used to flip the LVLH reference systems into the celestial inertial coordinate system. So what I've done is I've superimposed the coordinate systems on one another at the right. And you notice LVLH is in green and the celestial inertial is in purple. And what you can see there is there's a correspondence between the X celestial inertial and the Z LVLH, and one is related to the other by being the opposite of one another. So the X is related to minus Z, and you can go through a similar operation for the other one. And the reference change matrix just turns out to be nothing more than some ones and zeros and minus ones. And all it's intended to do is flip LVLH into the celestial inertial reference frame. So here's our aside here before we do our example problem here. If we're going to orient surfaces, it's really, really important to know, how it's oriented with respect to the sun, but also it's important to know how it's oriented with respect to the planet, because from the view factor to the planet determines our planetary infrared heating, and it's also used in part to determine what our albedo flux is. Now, if you took my Introduction to On-Orbit Thermal Environments course, you'll know the example that we did at the very end of that just had a nice orthogonally oriented cube where all of the axes were aligned in a way where we didn't have to get into any nasty orientations. So what I wanted to do here was introduce a general view factor equation that I got from the reference at the bottom here. And the geometry is as follows. You notice the spacecraft surface is in black. The surface is at some altitude h above the planet, whereas the distance to the center of the planet is the vector r. The radius of the planet is r sub p. Then we've got a couple other angles there, phi and theta. And what I'm going to do is give you a formula here. I'm not going to derive that formula, but if you want a general view factor to the planet from the plate, you give it as follows. You define the parameters this way. And I will point out, if you go to the source material on that the parameter definition for the lower kh and subsequently, which leads to uppercase h, what I present here is different than that in the reference. So I just wanted to point out, if you're noticing a difference between what I have here and what's in the reference, I had to define it a little bit differently, okay? But the nice thing about it is that we now have an expression for the view factor to the planet for the cases where pi over 2 minus phi is less than theta, which is less than pi over 2 plus phi. We've got the nasty expression. Otherwise, we've got the expression that's at the bottom there. And then if the plate is pointing away from the planet, obviously the view factor to the planet is 0, okay? So this is going to be important because we want to do all this attitude transformation. We want to be able to turn it into something thermal engineers can use. And you'll be able to plug some of the numbers that you get from that analysis into this view factor analysis to do something useful. So using h and the radius of the planet, we can determine what phi is, and then to determine theta, we'll also need the orientation of the spacecraft surface with respect to the planet, and we'll need to perform the attitude transformation. So that's where your inputs for this equation go from what we're doing today, okay? So here's our example problem. We're gonna put a spacecraft at a 500 kilometer altitude, circular orbit, eccentricity of 0, inclination 28.5 degrees. Argument, the right ascension of the ascending node 270 degrees. For a circular orbit, there is no low point of the orbit. Everything's at the low point, so the argument of periapsis is undefined. And we're going to make it March 20th, 2020 at 3:49 universal time, and that just happens to be the vernal equinox for this year. The solar flux is 1,371 watts per square meter. The albedo, which is just the fraction reflected of sunlight, is 0.3. Please don't get the lowercase a there confused with semi-major axis. A here is for albedo, and I always joke that there's more interesting things to study than there are letters in the alphabet, so sometimes we have to reuse them. And then the planetary infrared heating or outgoing long-range radiation heating I'm using here is 237 watts per square meter. So what our challenge or our problem is here is I've got a cubical spacecraft, and I'm orienting it such that it's pitched down 45 degrees with respect to the LVLH system. It's not yawed, it's not rolled, and it's an LVLH. And for the specified orbit and environment parameters, I want to determine the solar, albedo, and planetary heating flux on the surface that's pointing 45 degrees towards nadir, which means 45 degrees towards directly below or towards the ground from the velocity vector. The velocity vector is also called the ram direction. And I want to find out what these fluxes are as a function of time. I also want to determine the beta angle profile over time, assuming only this oblateness perturbation, and calculate the percent time in the eclipse. Okay, so again, using visualization from Thermal Desktop, this is our spacecraft here. You notice the plus x-axis faces into the velocity vector, and what I want to do is I want to pitch that down 45 degrees. Okay, I'll pitch it down 45 degrees so that surface will be facing 45 degrees into the velocity vector and 45 degrees down to the ground. You can see the untransformed reference position on the left. You can see the box pitched minus 45 degrees on the right, and it's the surface that where the red x-axis is coming out of it. So since the surface normal is pointing out the x-axis in the body coordinate system for the spacecraft, that unit vector is 1, 0, 0. It's 1 unit in the x direction, 0 units in the y and z. And we want to calculate the heating for this surface once it's tilted 45 degrees towards nadir. So we've yet to do the transformations on it, okay? So now we want to form the Euler angle sequence to transform that plus x facing unit vector to the prescribed pitch, yaw, and roll. And I execute the rotation sequence in this order first, a y-axis rotation because we're doing pitch, then a z-axis, and then finally an x-axis. Actually, the z and x-axis don't matter because those are both 0. And then I put in my minus 45 for pitch. Let me point out one other thing here. Since the yaw and the roll axis ones don't matter, when I put in zeros for those, both that blue matrix and that red matrix become the identity matrix. And you know, when you multiply something by the identity matrix, you just end up with the same thing. So I just want to show you how that those matrices aren't players if those rotations are 0. We also have to transform the Euler sequence to position the spacecraft within the reference frame. So you remember that large stack up of transformations from the LVLH reference frame. I need to transform right ascension, inclination, argument of para-apsis, and true anomaly. As I mentioned, for a circular orbit, the argument of para-apsis is undefined, so we put in a value of 0. That becomes the identity matrix as well. So we put in these other parameters. And remember, we've got to put in that reference change matrix, so I added that in orange there. And this is the math that we have. We transform that vector 1, 0, 0 through a 45-degree pitch, 0 yaw, 0 roll. We take it through the reference change matrix, and then we move it through the orbit based on the orbit parameters that were given. And the transform vectors that we have will be in the celestial inertial system. So again, here's our mathematical machinery that takes something we know in the spacecraft body, transforms it through its rotations, and transforms it into the celestial inertial coordinate system. So now what we also want to do is calculate the angle between the transformed surface normal and the center of the Earth, because we want to, eventually we're going to be calculating the view factor between that surface normal, that plate, and the center of the Earth, and we need to know what that angle is. So the vector that points from the center of the Earth out to the spacecraft is just what I'm showing you at the top, but we need a vector that points from the spacecraft to the Earth. So all we got to do is flip that one around. So I go from a 1 to a -1. And to calculate the angle between the transformed surface normal and the center of the Earth, all I have to do is take this vector, or take this vector that I just created, this -r vector, and I dot it with the transformed surface normal because they're both in the celestial coordinate system. And that gives me the angle. These are both unit vectors. So dotting those together gives me the cosine of the angle between them, or this will be the cosine of the angle to the center of the Earth. And then to calculate the angle between the transformed surface normal and the sun, we can calculate, we use the previously derived expression for the solar vector. Okay, so so now I know the angle between my transformed surface normal and the celestial inertial coordinate system and the transformed solar vector, and the dot product of those two unit vectors is the cosine of the angle between them. So for a flat surface, the view factor to the sun is just the cosine of the angle to the sun. If I have something pointing directly at the sun, it's going to get full solar flux. If I have something at a 45-degree angle to the sun, it's going to get cosine of 45 times the solar flux. Okay. So when I do that, I can calculate the angle from the unit normal to the center of the Earth and the sun. And what I did here is I just propagated this through the entire orbit. Okay, so since I know how the spacecraft moves in the orbit plane, I just go over the orbit period, and what this does is this tells me the angle to the sun and the angle to the center of the Earth. So let's do a quick does this look right test. What I would expect for an LVLH orbit is I'm in an orientation that's constant with respect to the planet, but varies with respect to the sun. So look at what happens. The angle to the center of the Earth is constant here. Matter of fact, it's 45 degrees, because I'm tilted down 45 degrees. And then the angle with respect to the sun changes throughout the orbit and would repeat after that orbit. And then at the bottom, I can use that information that I had to plug into that view factor equation. And you notice my view factor to the planet is constant. You notice that the view factor of the planet's about 0.6 something. I think for this altitude of orbit, the view factor, if the plate were facing the planet directly, would be at about somewhere around 88%. So that passes the looks right test. And then as I go around the planet, I would expect my view factor to the sun to change. Okay? So once I have those view factors now, I can take the solar flux times the view factor with respect to the sun with respect to time and multiply that out. I can do a very, very simple albedo model, which just says the albedo factor times the sun times the view factor to the planet, and then I scale it by the cosine of the angle between the sun and the spacecraft to do a simple albedo model. You can look at that in my introduction to on-orbit thermal environments. That gives me my albedo flux. And then I can do the outgoing long-wave radiation. That's just the view factor to the planet as a function of time times the planetary flux. And then you can see those fluxes at the right. So you can see I've got a constant planetary IR flux. I've got albedo flux that varies as a function of orbit angle. And for times where I'm not in the sun, the albedo goes to 0. And then you can see I've got the solar flux there as well. And I put in, I took account of the fact of when I'm in the eclipse based on what we calculated earlier. And you can see what the solar flux is. So there's an example of putting it all together and being able to calculate the heating incident on a spacecraft surface. I also went ahead and did the beta angle profile, and you can see how the beta angle profile varies over time. This is a 28.5 degree inclination orbit, so 28.5 plus about 23.5 tells me that the limits of my beta are plus and minus 52, and lo and behold, our beta stays bounded between plus and minus 52. And then since I do the beta angle over time, and since we don't really stray that far from low beta angles, you'll notice that my variation of time spent in sunlight or in shadow does not change much. There's periodic dips and bumps, but by and large, it stays relatively constant throughout the year. And this considers perturbations from the J2 term only. There's going to be other perturbations that eat your lunch in real life, like drag and all of that kind of stuff. But this is just there to give you an illustrative example of how you use these equations to get an idea of what's going on. So let me wrap this up here, and then we'll go in for questions. We focused on attitudes here. We looked at both local vertical, local horizontal, and celestial inertial. We used the reference frames and demonstrated an attitude transformation strategy, namely multiplying together gobs and gobs of Euler angles or Euler transformations. And then we used the transformation to orient the spacecraft surfaces with respect to solar, albedo, and planetary. And then we had that view factor equation to the sun and the planet, and we calculated and used those to calculate heating to spacecraft surface. I will just say, if you really want to understand the unordered thermal environment, you really need to know something about orbital mechanics and attitudes. So I hope that this has been a useful session for you. We focused on the two-body problem, but we gave a lot of examples of that are pertinent to thermal engineers. We introduced spacecraft attitudes and reference frames and their effect on the thermal environments. And all of that made good sense to you. I do want to take a moment here and thank Robin Beck of the Ames Research Center and Jack Herkel of Johns Hopkins Applied Physics Lab for reviewing the lesson. They pointed out a lot of things that I needed to clarify. So any errors that remain in here are all mine. I own that. Happy to fix them or clarify them over time. And I would just say, I sure enjoyed putting this together. I hope that you found it useful. I'm going to leave this up on the screen for a minute here. If anybody wants to correspond, the best thing to do is contact me by email. Obviously, we're teleworking these days, so my office phone isn't really being monitored. So the best way to reach me is at my email, stephen.l.rickman@nasa.gov. And with that, I thank you, and let me open it up for any questions that you have.
All right, we'll go through the questions really fast. Alyssa from Colorado is asking, what's the advantage of choosing the low vertical, low horizontal versus the celestial inertial coordinate system?
Excellent question. There's a lot of spacecraft that fly in a local vertical, local horizontal reference frame. So the space shuttle often flew in let's say like a payload bay Earth nose on velocity vector orientation, where the space station commonly flies in a local vertical, local horizontal orientation. So it's the way that the spacecraft flies, and then it's on our shoulders to do the transformations we need to get everything into the coordinate system that we need, namely the celestial inertial coordinate system, so we can do our calculations as thermal engineers.
And then Dan from Huntsville asks on slide 186, he sees P, Y, and R in brackets, and he was asking, isn't this really roll, yaw, and then pitch in terms of matrix multiplication order? Are you supposed to have aren't you supposed to have the first transformation closest to the vector?
So
I think he's saying that roll and pitch, should those be switched?
Roll and pitch. Well, the only thing it depends. It's different for different spacecraft. What I remember about the shuttle is the attitude timeline expressed it in terms of roll, pitch, and yaw, but they were executed, but we would understand that they were executed in a pitch, yaw, roll order. but the onboard software did roll pitch or pitch yaw sequences or something like that. So it's really dependent upon the spacecraft and the convention that's adopted. For this particular example, yaw and roll were 0. So it didn't really matter where I put them, but I'm just used to expressing it in terms of pitch, yaw, and roll. So I hope that answered the question.
And I think we have another question from Adam in Florida. He asked, whenever we perform Euler transforms, there is a risk of gimbal lock. Do you have any tips or rules of thumb for reducing these oriental ambiguities?
So if you're talking about gimbal lock in terms of guidance, navigation, and control, I have no background in that or the hardware of that. These mathematical transformations are purely for this thermal analysis. So presumably your mission planners are going to give you attitude sequences that are, that are representative of the spacecraft orientation. Whether there's gimbal lock or not has 0 bearing on the thermal analysis, but I agree it could be something that you'd have to consider for guidance, navigation.
And I see one other from Pune in India asking, why do we take the view factor to the central body and not from the central body to the orbiting body in the calculations? Is this due to dealing with the flux per unit area?
Exactly. It's exactly right. Because as engineers, when we get an environments document, that's an excellent question. As engineers, when we get an environments document, we usually get it specified for us what the fluxes are from the planet. So if I know the planet is giving off 237 watts per square meter in outgoing long wave radiation, then what I need to do is determine how well my plate or my surface my spacecraft surface can see that. So that's exactly the reason why you take the view factor from the surface to the planet.
Don't think I see any more questions. So let me say on behalf of TFAWS and all of us here, it has been an absolute pleasure, Steve, to have you. This has been a fantastic short course. Thank you for your time and for all of this information.
I am absolutely thrilled to be able to give it. I thank people for their interest in it. And again, if people have questions, I would invite them to correspond. But I absolutely loved doing it, and I hope everybody finds the information out.
There are lots of thank yous being sent out to you, so I do believe a lot of people are very grateful. And thank you to everyone for attending this course and being so respectful during and asking all your questions.
Thanks for people's interest. You made my day. It really is a big boost to see that it helps people.